يرفع الله الذين آمنوا منكم والذين أوتوا العلم درجات بسورة الجدل. بس اللي قبلها واللي بعدها شو اسمه مش يعني
may I have your attention, please? Okay. Sorry for the delay. We apologize for that. We are waiting for the Minister of Education, Higher Education, who will be joining us shortly. So we'll wait approximately 10 minutes. Thank you. Yeah, yeah. صباح الخير للجميع. Good morning to everyone. I would like to ask everyone to please be seated as we're going to start the opening ceremony for this conference. Bismillah ar-Rahman ar-Rahim. His Excellency Dr. Sabri Saidam, Minister of Education and Higher Education in Palestine. His Excellency Dr. Ali Sudan, President of the Arab American University in Jenin. Dr. Adli Saleh, Chairman of the conference and former President of the Arab American University. Mr. Kamal Abu Rab, Deputy Governor of the Jenin Governorate. Invited speakers and guests, members of the audience, and students. On behalf of the organizing committee, it is my pleasure to welcome you all at the 5th Palestinian Conference on Modern Trends in Mathematics and Physics. The conference provides opportunities for Palestinian scholars, to meet and exchange views and explore collaboration with international scholars and locally among Palestinian universities. It also exposes our students, graduate students who are doing research in their programs, to meet with international scholars and be exposed to an international conference. It is also a great honor to welcome you at the Arab American University. The Arab American University is the first Palestinian experiment in private education, with the unprecedented determination of its founders and investors, the vision of the founding president, Dr. Walid Deeb, who is a mathematician, the hard work of the employees and staff. Okay. It started 16 years ago with some 200 students in this previously remote area with essentially no infrastructure. It grew against all odds and restrictive occupation of movement. It hosts now over 10,000 students in 8 colleges, 8 faculties, and about 48 programs. To our guests from abroad, it is also an honor to welcome you in Palestine. We appreciate the effort and the courage to travel to this region to attend this conference. We hope you feel the warmth and welcome in Palestine, and we wish your stay will be enjoyable, productive, and memorable. It is customary in Palestine to start such a great event with verses from the Holy Quran cited to us by student Muhammad Hilmi.
أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. تبارك الذي بيده الملك وهو على كل شيء قدير. الذي خلق الموت والحياة ليبلوكم أيكم أحسن عملا وهو العزيز الغفور. الذي خلق سماوات طباقا ما ترى في خلق الرحمن من تفاوت فارجع البصر هل ترى من فطور ثم ارجع البصر كرتين ينقلب إليك البصر خاسئا وهو حسير. ولقد زينا السماء الدنيا بمصابيح وجعلنا وجعلناها رجوما للشياطين وأعتدنا لهم عذاب السعير. صدق الله العظيم.
صدق الله العظيم. As a representation of Palestinian aspiration and yearning for independence and freedom, it is also customary in Palestine to play or to begin this event with the national anthem. And for you, I would like to ask you all to please stand. And finally, this morning, a moment of, please remain standing, sorry. A moment of silence and a prayer in respect to the Palestinian martyrs. We have three distinguished speakers to start this opening ceremony. The first speaker is Dr. Adli Saleh, the chairman of the conference and former president of the Arab American University, a long-time colleague and a friend. He has a PhD in physics from Montana State University, worked at Charles and Associates in California for several years before joining the Arab American University in 2003, became vice president for planning and development for 2 years, and then its president 2007 until 2012 or 2013. Without further introduction, please welcome Dr. Adli Saleh.
بسم الله الرحمن الرحيم والصلاة والسلام على أشرف الأنبياء والمرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Your Excellency Dr. Sabri Zina, the Minister of Education and Higher Education, Your Excellency Professor Dr. Ali Zidan, AAUJ President, respected representative of Jenin Governor, Mr. Kamal Abu Rub, respected conference participants from abroad and from Palestinian universities, my friends, colleagues, and students from AAUJ. I welcome you all to the 5th Palestinian Conference on Modern Trends in Mathematics and Physics that's being held here at the Arab American University in Jenin, Palestine, for 3 days starting today. It's a great honor to be the chair of this prestigious conference in its 5th cycle, which over the last 10 years has become the focal point for scholars and graduate students in the areas of physics, mathematics, and statistics. Over 120 contributions will be presented during the course of the conference by scholars from across the globe and from here in lovely Palestine. A special volume of the AAUJ Scientific Journal will be dedicated to these contributions after the conference is over and after the customary review process. It saddens me to tell you that many of our friends and colleagues who contributed to the conference will not be able to present their work. Scholars from Gaza were not issued travel permits by the Israeli occupation to travel to Jenin, thus denying them the right to be with their colleagues at this important Palestinian scientific event. Also, my friend and colleague, Professor Dr. Imad Barghouthi, with a paper submitted to this conference and a presentation to give, is still detained and is still denied freedom and continues to be detained by the Israeli occupation forces. We continue to fight for freedom and hope that we will one day have independence. We call on the international community to press for ending the last occupation on the occupation of Palestine. I take this opportunity to thank the university administration, represented by Professor Dr. Ali, the president of AAUJ, for the great trust and support I was given. And to my friends and colleagues, the members of the many committees which made this conference a reality. The names and titles are listed at in the conference booklet that I presented to you earlier. Finally, I wish you a memorable and eventful meeting. I thank you again and welcome to AAUJ.
Shukran, Dr. Adli. Next, we'll listen to a word from our university president, Professor Dr. Ali Zidan, a long-time associate and friend also. Dr. Zidan has extensive experience in higher education that cannot be fairly covered in this brief introduction. He has a PhD in chemistry, served as Vice President for Academic Affairs in year 2000 to 2002 at AUJ, left to become the President of Al-Aqsa University in Gaza for several years, held at least 2 ministerial positions for education and communication before rejoining Arab American University as its president last year. Without further introduction, please welcome Dr. Ali Zidan.
Bismillah ar-Rahman ar-Rahim. Your Excellency Dr. Sabri Seda, the Minister of Education and Higher Education, respected representative of Regime Governance, Mr. Kamal Abu-Rub, respected conference participants from abroad and from other Palestinian universities, my friends, colleagues, and students here at AUG. Assalamu alaikum wa rahmatullahi wa barakatuh. I would like to welcome you all to Arab American University in Geneva, Palestine. Our university is honored to host a Palestinian conference on modern trends in mathematics. This stems from our commitment to excellence in teaching and research. We also strongly believe that partnership with international organizations that aim to help our faculty and students attain edge knowledge will further strengthen our positions as providers of state-of-the-art education. Last week, AAUJ hosted the first advanced physics school in partnership with Scientists for Palestine for the benefits of students, graduate students from Palestinian universities in area of physics. The Palestinian people, while they continue to aspire to be free, place a very high value on education, particularly in the area of science and technology, to realize their full potential as a nation and to build a modern and democratic state. Despite the difficult challenges Palestinians faced over the past several decades, they made a great contribution throughout the region and the world over. From last few days, the Israeli occupation prevent a football team to come from Gaza to the West Bank to play match with Hebron clubs. And today, as Dr. Adli mentioned, they prevent the scientists from Gaza University to participate in this conference. Enrollment in university education is over 10% higher than the average for the Arab region. And half the students are women, a ratio among the highest in the world. Our university will pleased to support such efforts in the future and will partner with national and international institutions to organize summer schools to enhance the teaching of science in general. Also, finally, I would like to thank the organizing committee for this conference, especially Dr. Adli, and I thank you and welcome you again. Thank you.
Thank you, Dr. Adli. Finally, for this opening session, it is my pleasure to introduce our Minister of Education and Higher Education, His Excellency Dr. Saidan. In spite of his younger age, his experience is also too long to cover in this introduction. He has a electrical engineering from Imperial College in London, served as an advisor to the President and then Minister of Telecommunication, Information Technology and Technical Education. He helped launch the .ps domain and its governing body before assuming his current position as Minister of Education and Higher Education. Without further introduction, please join me to welcome our Minister of Education, Dr. Sabri Saidan.
Bismillah ar-Rahman ar-Rahim, Sabah al-Khair. I was asked by Dr. Ali to use his speech. I could use a version in Arabic of his speech, but I would rather use my own speech to tell you good morning. The reason I'm here is to support you and to show interest in what you're working on, especially given the fact that there's international trends that interest in physics and mathematics is not as one would desire. During my years as a physicist, there was dwindling numbers of people interested in joining physics, and people were asking as to what are the trends that ought to be adopted by the world. So this situation is modified and is taken into consideration vis-a-vis increasing the number of students and children interested in joining such streams and such disciplines. And I say that this is a question that's concerning every child around the world and every young man and woman in joining physics and mathematics. The big question is how to make physics and mathematics interesting subjects so becoming the center of attention and really be transcended into the fact that they are the true representative of science. They're the core and backbone of science and scientific disciplines. It's not an easy thing to consider. It's something that needs a lot of attention and needs a lot of emphasis on the way forward and on discussions of this magnitude and on conferences to look at best international standards and see as to how we can collectively put some emphasis on this factor and consider them into our work so that they are represented and reflected in our school curriculum and maybe in the curriculum in the universities and methods of teaching for sure. In a few days' time, we will be releasing the new version of the Palestinian school curriculum, grades 1 to 4. And with that comes, I would say, what we consider to be part of the answer, whereby we focus on giving guidance to teachers and allowing their imaginations to lead students into focusing on education in physics and science vis-a-vis gaming and learning by doing. And as I could see some heads nodding in agreement, I would say this is dependent on the competence of the teachers and their capabilities to handle such work. It's not easy. It's something that needs a lot of training and a lot of pressure, I would say, from different directions on improving the qualities and capabilities of teachers. With me today are my colleagues representing the stream within the ministry that looks at the supervision of teachers and cultivates the capabilities of their teachers, of our teachers, in a way that they become more entrenched into the use of physics and mathematics, turning them into subjects of interest, and also applying games and applying concepts of deep learning, interactive learning, and analytical thinking being applied ride into the trends of using mathematics and physics as the way forward. I very much enjoyed physics at the time, but that was dependent on my teachers. The subjects that I hated for sure as a student, and now, a few years ahead of the time, I can look back and confess to few factors. At the time, there was a teacher or a lecturer who was very interested in the work he or she is doing. That showed an interest on the part of the class, using different methodologies in delivering the concepts really helped in consolidating these concepts and the principles of matters that were of interest. So I think there's a lot that will come out of this meeting. Sorry that time will not come to my service or to my rescue into spending a sufficient amount of that time with you to see how things are flowing. I assure you I will be following the work of this conference and the outcome with great interest to see what can be used in our work. And that's the idea. We see the work of higher education institutions as complementary to the work of educational institutions and departments within the ministry, so to improve the quality of work and make sure that we put energy into practice and we put principles into implementation. That's a factor that ought to be considered, and this is how complementary work is taken into consideration and help consolidate the work we are doing. Very much happy that this university is armed with its esteemed colleagues who are interested in this matter and armed with interest and leadership that shows the importance of looking into matters of this magnitude and seeing international partners whom were warmly welcomed by our people here to also shed some light on the work that ought to be done. سعيد فيكم جميعا. اسمحوا لي أن أقول أعتدت في مناسبات عديدة في لقاءات مع الجامعات أن أحمل معي أخبارا طيبة حتى يسعد رئيس الجامعة زميلي وزير التربية والتعليم العالي سابقا، كما قدم وزيرا كان للاتصالات، أنه كان وزيرا للمواصلات، وأيضا زملائي على المنصة دكتور عدلي وعريف الحفل العزيز رئيس المؤتمر والجميع كل الأحبة. بهمني أن أقول أنه إحنا دائما نحب أن نحمل الخير لكم بهذه المناسبة وبهذا المؤتمر. يسرني أن أعلمك دكتور بموافقة وزارة التربية والتعليم العالي على اعتماد برنامج إدارة الجودة الذي انتظرتموه طويلا. To our international friends, that wasn't to backbite you in any way. It was to say that we have approved one of the programs that has long been overdue approval in the ministry's drawers and shelves. So now it's been endorsed, and hopefully we will see its implementation into the the usual university program. I would say this is about quality assurance, and indeed what we are seeking and soliciting today is an interest in quality assurance in science and physics teaching. يسعد الله جميعا. شكرا ويعطيكم ألف عافية. أسف إنه الوقت لا يسعفني للبقاء معكم، ولكن سأتابع تفاصيل هذا المؤتمر إن شاء الله حتى نستفيد من هذه التجارب. شكرا، أسعد الله صباحكم. يعطيكم العافية.
Shukran, Dr. Sabri Saidam, for this support for the university and for the conference. We appreciate that. This concludes our opening ceremony, and we will have a break, 15-minute break. So we'll be back here for the plenary session at about, let's say, 10:20. Okay, so we'll be back here in this room at 10:20 for the plenary session. Thank you.
I look forward to, as do my colleagues and students, look forward to this presentation. Thank you, and please, the podium is yours.
So thank you very much for this invitation to the conference, to Professor Adley and his colleagues. And it's a pleasure for me to be back in Palestine, pleasure for me to be back in Jenin. And what I'd like to do in this talk is to share with you some of the recent and possibly future developments in particle physics. So on the screen behind me, you see the Large Hadron Collider at CERN. So it's large, it's 27 kilometers in circumference. Here over on the right-hand side is the runway of Geneva Airport, just to fit the overall scale. So as I'm sure you know, 4 years ago, a major discovery was made at the Large Hadron Collider, namely the Higgs boson. And this here is a picture of Peter Higgs back in 1965, shortly after he proposed his theory. Here he is working out all the details. So I want to provide you with a little bit of background to that discovery by reviewing the standard model of particle physics. Then I'll talk about the discovery of the Higgs boson itself, and in the last part of the talk I'll discuss what other new physics there may be. In fact, we expect that there will be additional physics beyond the standard model, beyond the Higgs boson. Just to fix ideas, here is the range of scales we physicists discuss, all the way from the size of the universe today, about 10 to 28 centimeters, down to the smaller scales that we theoretical physicists speculate about, 10 to the minus 32 centimeters. And somewhere about halfway along, we have a human scale. So here's a picture of Albert Einstein and his kid sister when they were about 1 meter tall, about halfway along this logarithmic scale of physics. Of course, we understand a lot about what went on inside Albert Einstein and his kid sister. Molecules, atoms. Atoms contain nuclei with clouds of electrons around them. Nuclei are made up out of protons and neutrons. And inside the protons and neutrons, we have quarks. So the business of we particle physicists is to understand better the quarks, the electrons, the particles, and the forces between them. Now, there's actually a very close connection between what we're trying to do and some of the most basic problems in cosmology. One example, as I'll discuss in more detail later on, one of the biggest mysteries in cosmology and astrophysics is the origin of the dark matter that holds structures and galaxies together. And that dark matter may be particles, possibly particles that we can make at the Large Hadron Collider. Of course, our core business, if you like, is to look down deep inside the proton, inside the quarks and electrons, and accelerate off the Large Hadron Collider is, of course, primarily a supermicroscope, but in some sense, it's also a telescope addressing fundamental problems in astrophysics and cosmology. Now, in the first half of the 20th century, many of the discoveries in particle physics were made in cosmic rays. So here's a picture of Victor Hess, who in 1912 discovered that there was this radiation, these energetic particles hitting the Earth from outer space, and these some of them have extremely high energies. Those energies are converted into other types of particles, and many fundamental discoveries were made by looking at the showers of particles produced by those cosmic rays. But around the middle of the last century, physicists realized that if they wanted to understand in detail the properties of those particles and their interaction, then they needed to do controlled experiments in the laboratory using known beams of particles of known energies. And so accelerator physics was born, and this has its current in the Large Hadron Collider. So what did those studies reveal? So they revealed the correctness of what we call the standard model of particle physics. The standard model was proposed in the 1960s by Abdus Salam here from Pakistan, and two American colleagues and Weinberg. And their theory makes essential use of the ideas of Peter Higgs and colleagues that I'll be discussing in a moment. So the first evidence in favor of new physical phenomena predicted by Abdus Salam and colleagues was in 1973 in experiments at CERN. And if you come to CERN, you'll be able to see the apparatus used to make this discovery. Followed by very detailed evidence at CERN and other particle physics laboratories that verified the predictions of the standard model in great detail. I don't know whether you can make it out on the screen, but here there's a tiny little dot, and there's a green line here. The green line is the theoretical prediction, the dot is experimental measurement. The standard model works incredibly well. So what does it actually consist of? So I mentioned quarks, the constituents of protons and neutrons. We know now that there are 6 different types of quark, which I've indicated over here on the left-hand side of the slide. I talk about electrons. So we know that there are 2 heavier electron-like particles. There's a muon, one of the particles discovered in cosmic rays, and there's the tau, which was discovered in particle accelerators later on. And then in between we have neutrinos, postulated in the 1930s, discovered in the 1950s. I'm not going to say much about neutrinos in this discussion. So between these fundamental particles, we distinguish 4 different fundamental interactions. So over on the left here, we have gravity, which keeps even theoretical physicists firmly on the ground. We have electromagnetism, used by James Clerk Maxwell when he was a professor at King's College London 150 years ago. And then on the right-hand side, we have the strong and weak interactions. So strong interactions between quarks are carried by particles called gluons, much like photons in a way. The weak interaction is carried by particles called W, which are very heavy. And that is why the radioactive force is weak. So I like to think of what you see on this screen somehow constituting the cosmic DNA, which contains all the information needed to build all the visible structures in the universe, ranging from stars to Donald. It was supposed to be a joke, but maybe it isn't. Okay, so actually there's one piece of information which is missing, which is where particle masses come from. So for example, the electron has to have a mass. If it didn't, we would never have any atoms, because electrons would fly away from nuclei at the speed of light. And this particle here, W, which is responsible for the weak nuclear force, I mentioned, it has a very large mass, it weighs as much as a medium-sized nucleus. Where does that mass come from? And it's important to answer that, because if that particle didn't have a mass, radioactivity would be as strong as electromagnetism, and life would be impossible. So, we all learned in high school that weight is proportional to mass, and Einstein told us that E is equal to mc squared. Unfortunately, these gentlemen never explained where mass comes from in the first place. They related other things to mass, but where does mass itself come from? And that is the problem that was solved for particles by Peter Higgs and colleagues in 1964. And well, there's details of his theory on the board behind him, but I won't discuss that in detail. The key aspect which I want to talk about now is the fact that according to this theory, there should be a new particle called the Higgs boson. So you can make out there's a thing called phi, that's a field, and like any other field, like the electromagnetic field, there's a particle associated with the Higgs field, and that is the Higgs boson. Yeah, he was a student at King's College London. I promise you I won't advertise King's College London anymore. So when I'm talking to a very general audience, students maybe, I try to explain the Higgs idea through an analogy. And you should think of this Higgs field as constituting a universal background, an environment, a medium through which particles have to pass. So let's imagine that we're in the middle of Siberia in the winter. So we have snow everywhere, homogeneous, isotropic medium of snow. And we want to try to propagate through that snow field. So if we're lucky, we may have skis, and then we skim across the top of the snow, not interact deeply with the snow. We go very fast. That's a particle that does not interact with the Higgs field, the Higgs background. The particle travels at the speed of light, a photon maybe, no mass. On the other hand, maybe we've got snowshoes. If we've got snowshoes, we go more slowly, we sink into the snow, we interact with that background Higgs snow field. We go slower than the skier, less than the speed of light. So that's like a particle with mass, an electron. And then finally, maybe we are trying to walk through Siberia in our shoes. Then we're going to go very slowly because we're going to sink very deeply into the snow. We're going to interact very strongly with that Higgs snow field. We're going to be like a particle traveling much less than the speed of light, a very heavy particle. So that's the basic idea. You've got this universal medium, and your mass is proportional to how you interact with that Higgs snow field. What is snowflake? Snowflakes. Right. So correspondingly, what is the quantum of this Higgs snow field? It is the Higgs boson. And that is a particle which was recently discovered at CERN. Now, an interesting point here is, of course, there's many different types of snowflake. That's because they're objects made up out of water molecules arranged in different ways. And in the same way, particle physicists are arguing about whether the Higgs boson that was discovered at the LHC is perhaps a composite particle and not an elementary particle, as was originally in the theories by Peter Higgs collaborators. And I'll come back to this point later on. So now I want to describe this in a somewhat more mathematical way. So I want to come back to Nambu. Nambu was the person who introduced the idea of spontaneous symmetry breaking in physics. Physics, of course, previously it had been used in condensed matter physics. So here is a picture of the effective potential of the Higgs field, and it has this Mexican hat form. So the origin, where the Higgs field is 0, that's unstable. The stable configuration is around the brim of the Mexican hat. Now, of course, different points around here are equivalent. They have all the same energy. That means that there is a matchless degree of freedom corresponding to rotating around the bottom of the Mexican hat. And that's what's called the Nambu-Goldstone boson. Now, what Peter Higgs, Englert, Braut, Koenig, Hagen, and Kittel did was that they added to this system called a gauge boson, much like the photon. And I won't go through the detailed mathematics of it. What happens is that this massless Nambu-Goldstone boson running around the bottom couples with the massless photon-like particle, and the combination is a massive vector particle. Now, that idea of spontaneous breaking, as I said, was proposed by several authors back in 1964. The crucial thing that Higgs mentioned in his paper is that there is an additional degree of freedom in this system corresponding to this radial oscillation here. Now, since that changes the energy, it corresponds to a massive particle, and that massive particle is what we call the Higgs boson, and that is what was discovered in 2012. So my own personal interest in this started some years later in 1975. People were beginning to have evidence for the model, and together with my colleagues Mary and Anopoulos, we set out to think what a boson might look like in an experiment. In those days, this was all regarded as exceedingly speculative, and so we were a little bit cautious in our paper. We wrote, we do not want to encourage big experimental searches for the Higgs boson. Fortunately, our experimental colleagues went ahead anyway. So this is a picture of the Large Hadron Collider. So I told you earlier on has a distance of 27 kilometers. It's actually a tunnel on average about 100 meters underground, so you don't see very much from an airplane. And these tubes here, these contain magnets cooled to a very low temperature. The particles go inside those magnets and make collisions. So when it's in operation, you've got billions of protons going around. Each one has approximately the energy to fly, and in full operation it makes perhaps a billion collisions per second. So a few years ago, if I'd been describing to you what we were trying to do with these experiments, I would have said, well, we want to understand the origin of particle masses. We want to understand the nature of dark matter. As I mentioned, matter might be made of particles we can make at the LHC. We want to understand what happened in the very early universe, the primordial plasma. I'm also interested in the difference between matter and antimatter, which may explain the predominance of matter in the universe today. So I'll come back to that and the nature of dark matter later on in the talk. Of course, we believe that we discovered the origin of mass, so we can tick off the first objective. Right now, the Large Hadron Collider is operating at a higher energy than the first one that discovered the Higgs boson, and so we have reason to think that we might be able to make progress on some of these other issues. So this is a picture inside an LHC magnet. Inside the magnets, we have tubes that the particles go around, and we have to have an extremely good vacuum inside those tubes in order that the particles hit each other and don't hit molecules of gas. So that the vacuum inside those tubes is lower than on the surface of the moon. In order to go to very high energies, we need strong magnetic fields. We need cryogenic magnets. Those magnets are actually cooler than outer space. So outer space is 2.7 degrees above absolute zero. Magnets are 1.9 degrees above absolute zero. So I like to tease my cosmological friends by telling them that particle physics is 0.8 degrees cooler than cosmology. Okay, so we've got the particles going around, we've got them colliding, and then we need detectors to observe what is produced. So there are 4 major experiments at the LHC. There's ATLAS and CMS. Those are the big detectors to discover the Higgs boson and are now looking for particles of dark matter. ALICE, which is trying to understand the primordial cosmic plasma, and LHCb, which is trying to understand the difference between matter and antimatter. So I'd like to highlight the fact that the Atlas collaboration now contains quite a number of young Palestinian physicists, mainly working with institutes in Europe. Some of them, at least one of them, has now come back to Palestine and is sitting somewhere in the audience. I'll come back to the involvement of Palestine in some research at the end of the book. Okay, so primary objective of the LHC was to discover the Higgs boson, and here I show you various ways the Higgs boson might be produced. The dominant mechanism is actually guiding pairs of gluons inside the proton, and that is a cross-section which falls as a function of the possible mass of the Higgs boson. It actually turns out, fortunately, that the mass of the Higgs boson is relatively small. It's about 125 GeV, and so we can also observe these other ways of producing the Higgs boson. So one thing is to produce the Higgs boson, the other one is to actually detect it. Now, the Higgs boson is an unstable particle, it's a neutral particle, so it doesn't leave a track. You don't see it directly. What you have to do is to look for the visible particles into which it decays. So in this graph here, I show you some of the ways in which the Higgs boson can decay. So I mentioned earlier on that the mass is about 125 GeV, and in this case there are many different decay modes which can be observed, which have been observed, and this is what's enabled us to be pretty sure that the particle that we've discovered is indeed the Higgs boson. Now, I might just mention one interesting fact, which is that the dominant way of producing the Higgs is through gluons. One of the clearest decay modes that we calculated back in 1975 is to get to 2 photons. And those are actually quantum processes going through loop diagrams, which means also that as soon as we discover the Higgs boson, already probing its quantum size. I'd like to mention again the fact that because it was to be around 125 GeV, it was possible very quickly to identify many decay modes, production modes of the Higgs boson, and learn a lot about it. So this is one computer simulation of one particular way in which the Higgs boson might be observed. So in this case, there's a proton collision, thousands of GeV of energy, hundreds of particles produced, charged particle tracks are yellow, neutral particles deposit energy in these blobs. So what you can see over here on the right side are 2 very straight lines and large blobs. Those correspond to energetic particles depositing lots of energy in the detector. And 2 more straightish particles over there. So the straight particles correspond to energetic particles going through the magnetic field, and the 4 energetic particles together are the decay products of a Higgs boson. So now let me look at the actual discovery. And I think it's fair to say that when the Higgs boson was discovered back in 1912, there was what may be described as mass Higgsteria amongst particle physicists. So the discovery was based on observing events, like for example this one here. So the previous one that I showed you was simulation. This is a real event, a computer reconstruction. So when you see the charge tracks below, the deposits of energy, and you see 1, 2, 3, 4 very straight lines corresponding to energetic particles that might have been produced by the decay of a Higgs boson. So this is another example. In this case, you see a big red blob of energy here, another big red blob over there, but no track. So those are neutral particles, very energetic, probably photons, perhaps the Higgs boson. So it was observations by both the ATLAS and the CMS experiment of many events of those types that enabled us to announce on July 4, 2012, the discovery of a new particle. And this is the scene in the auditorium when the discovery was announced. And I would like to pay particular credit to Christopher William-Smith, who was the Director General of CERN, who got the Large Hadron Collider approved. Currently, by the way, he's President of the Council of the Sesame Project in Jordan. And Lynn Evans, who was a guy who actually built the accelerator. So this picture is interesting. So on the right, we have Peter Higgs. And here we have Francois Englert, who was one of the other theorists who proposed these ideas of spontaneous symmetry breaking. So they proposed these ideas back in 1964. But they never met until that day in 2012, 48 years later. This is a moment when the two inventors of the theory met. So that's one reason why I like the picture. The other reason why I like the picture is that here you see Fabio Totti was one of the announcers of the discovery that day, and is now the Director General of CERN. I'm looking in particular at the just fluctuation of the data, no significant signal. If I remove the blind here, you see a highly significant peak, no doubt a new particle. Now, when this particle was discovered in 2012, there was still obviously some room for doubt as to whether this was really the Higgs boson emerging from the background, and much of the effort over the following 2 or 3 years was devoted to trying to understand whether this object had the characteristics of the Higgs boson. We now know the mass very accurately. It's about 125 GeV, and the precise value of mass is actually very important for understanding the future of the universe, as I will discuss in a few minutes. Okay, so we've got a particle, we know its mass, but is it really the Higgs boson? Is it possible that it's some imposter pretending to be the Higgs boson? So I like to go the path of particle physics as being like a jigsaw puzzle, starting in 1897 with the discovery of the electron. 150 years later, you discover this new particle. Is this really the thing that completes? So together with my then PhD student, Tivong Yu, we asked ourselves the question, does this new particle actually couple with other particles proportional to their mass? If it's responsible for masses, its coupling to other particles should be related to the mass. So the standard model prediction is shown by this red line here, and these bars, those are the experimental data, and the experimental data are completely consistent with the idea that this particle has masses to the others. And for that reason, we wrote in our paper that this particle walks and quacks like a Higgs boson. Recently, this has been done more professionally by a collaboration between ATLAS and CMS, and their data again confirm that this particle couples to other particles proportional to their masses. Now, I mentioned earlier on when I talked about the analogy between the Higgs and a snowflake, the fact that a snowflake is a composite object. And as I also mentioned, there's now a lot of discussion taking place as to whether this particle is a or whether it's composite. So there are issues if it's elementary when you try to calculate loop effects. And when we try to control those quantum loop actions, one of the theories that we propose for obtaining the divergences is the theory of supersymmetry. I'll come back to supersymmetry a little bit later in connection with dark matter. The alternative would be to say that this particle is composite, like for example, a Cooper pair in superconductivity. Superconductivity is also due to spontaneous symmetry breaking. In that case, the order parameter is composite. It's the condensate of Higgs pairs. So people try to construct similar models for elementary particles, but they're not very successful. And moreover, the now tell us that this particle that was discovered in 2012 has no signs that it's composite. It looks elementary. So this again taken from analysis of my PhD student. We looked at the couplings to bosons parameterized by A, to fermions parameterized by C. So in standard model, A and C should be 1. Standard model puts the green star here. And the shining screen here, that corresponds to the experimental measurement of Higgs into bottom quarks, tau leptons, photons, W particles, Z particles. You put everything together, all the data are consistent with the standard model green star, and these yellow lines here, these correspond to alternative models. So, okay, you could tune a composite model so that it looked like the standard model, but the data give you no indication. This. So the Higgs boson is important. As I mentioned, if it didn't exist, electrons would have mass, there would be no atoms, there'd be no heavy nuclei, the weak interactions would be weak, life would be impossible. So the existence of the Higgs boson is certainly a big deal. And this, of course, is recognized by the Nobel Prize Committee in 2013 when they gave prize to Peter Higgs and François Blair. And in their citation, they said, beyond any reasonable doubt, this new particle is the Higgs. My student and I were rather proud because this quotation was taken from our paper. However, what the Nobel Prize Committee did not know is that this phrase was in the preprint version of our paper, but not in the published version. The referee of our paper said, beyond any reasonable doubt is not a scientific statement. So, not good enough for the journal, but good enough for the Nobel Prize Committee. So, is there any physics beyond the standard model? So, I would like to paraphrase James Bond and say that the standard model is not enough. The additional physics beyond the standard model. And in reference to James Bond, I give you 007 reasons for thinking there must be physics beyond the standard model. One is the problem that I mentioned briefly earlier on, the fact that according to measurements of the Higgs mass and the top mass, our electroweak vacuum looks like it's unstable. The universe will collapse in the future. I don't believe that, right? We believe that something will prevent our universe from collapsing, and that something has to be settled by physics. We need to understand the dark matter. We need to understand the origin of the matter in the universe. We would like to understand what neutrinos had small masses, the ratios and scales in physics. We'd like to understand why the universe is large. There's a theory called inflation, which lies beyond the standard model. And we would like to make a quantum theory of gravity. So, lots of fundamental problems to solve. I would argue that many of them are at least mitigated by the theory of supersymmetry that I mentioned briefly earlier, and I'll come back to in a moment. And the good news is that with run 2 of the LHC, experiments are now tackling many of these issues. So let me talk a little bit about the future of the universe and also about the past. So I have a plot, horizontal axis, mass of the Higgs boson, vertical axis, the mass of the top quark. Now, our current weak vacuum, the vacuum of the universe is unstable in this upper region here, and it's stable in this lower region. The data indicate that we're in this unstable region. As I said, I don't believe that for a moment. I don't believe that the universe is going to collapse tomorrow. I would like to say I don't believe that Donald Trump is going to get elected, but that I'm not so sure about. But I am sure the universe is not going to collapse, and therefore I think that we need new physics. So, let me describe a little bit what the problem is. So I drew earlier on that Mexican hat potential. So in the Mexican hat, the potential goes up to infinity. Unfortunately, when you calculate quantum effects, it's not true. The brim gets turned down like that. Now currently, we're sitting over here with a small value of the Higgs field. That value of the Higgs field is not the only one. Down here at the bottom, we've got a much larger value of the Higgs field, and the universe, as I said, would collapse. Now, the Higgs field is subject to quantum fluctuations. But in principle, cause us to tunnel through the barrier now. That will give you a decay vacuum in the future, the end of the universe as we know it. On the other hand, if you go back when the universe was very young, those quantum fluctuations would have been much larger, and it's possible to understand why we are still here and not over there. So for that reason, I think there has to be some sort of new physics to prevent the universe from collapsing now and to ensure that we finish up in the vacuum where we are today. And that new physics could well be supersymmetry. So another motivation for supersymmetry is provided by dark matter. So as I'm sure most of you are very familiar, the idea of dark matter has been around for something like 80 years now. It was postulated by Fritz Zwicky here, who observed that galaxies in the Coma cluster were going around very fast, much larger than you'd expect from the virial theorem. So he said, well, there has to be some additional source of gravitational field. Gravitating stuff, so-called dark matter. 3 more minutes. Okay, it looks to me like he's telling me it's 0 minutes. So the idea of dark matter, I think, was confirmed for many people by Vera Rubin, who observed a similar phenomenon with galaxies, that the stars going around galaxies didn't seem to obey the virial theorem unless you postulated additional dark matter. So it's possible that that dark matter is made up out of particles, maybe supersymmetric particles. Now, I don't have time to discuss supersymmetry in all its detail. Suffice to say that it postulates that in parallel to the standard model particles, there is a whole bunch of partner particles, and the lightest of those partner particles could provide the dark matter. So it's possible that those dark matter particles might be produced at the LHC. If so, you wouldn't see them. They would just carry away energy and momentum, like in this graphic over here, where there's a whole bunch of particles coming out there, but none on the opposite side. Dark matter particles carry away energy and momentum invisibly. And the experiments are looking for such events, but so far they haven't found any excess. How about the origin of the matter in the universe? So this is actually why we study antimatter physics. We're not interested in powering up the Starship Enterprise or blowing up the Vatican. What we're interested in is the difference between matter and antimatter, which we think may be linked to the origin of the matter in the universe. So Dirac, of course, postulated antimatter in the 1920s, particles with equal mass but opposite electric charge from regular matter, and the first antimatter particle, the positron, was discovered in cosmic rays a few years later. It came as a big surprise to everybody when it was discovered that matter and antimatter are not quite equal and opposite, and this may possibly be the reason why matter dominates over antimatter in the universe today. This was suggested by the Russian physicist Sakharov, whom you see here visiting CERN. So he said, well, if you have a difference between matter and antimatter, and if you have forces that can create matter, and if you have the expansion of the universe, put those ingredients together and you can generate a matter-antimatter asymmetry. So currently we're trying to put details onto that theory, in particular using experimental results from CERN. So the final physics topic that I wanted to mention is unifying the fundamental interactions. So this, of course, was Einstein's dream. Here you have him dreaming. Unfortunately, he never succeeded in making a unified theory, which is maybe why he looks a little bit sad in this picture. But one of the theories that he worked with was the idea that there might be additional dimensions of space, and this has become very fashionable in recent years with string theory. Now, in some of these theories with additional dimensions of space, gravity can become strong at the LHC energy scale, and you might be able to make microscopic black holes. So this got some people worrying that those black holes were going to eat up the Earth, but don't worry, the same theory that suggested they might exist tells us that they decay instantly, and anyway, if they existed, they would have been made by cosmic rays, and we're still here. So if cosmic rays are not dangerous, LHC isn't dangerous either. So this is a sort of roadmap of unification. So it was started off with Maxwell 150 years ago, progressed to the standard model of Abdus Salam and collaborators. Maybe the next step is supersymmetry. Maybe eventually we're going to unify using string theory. So that brings me to the end of what I want to say about progress in particle physics. But if I have 1 minute, I just wanted to say a little bit about Palestinian particle physics. So this map here shows you the origins of physicists registered to work at CERN. There's about 12,000 people here from just over 100 countries, and I'm very happy to say that Palestine is also here. So the blue countries are members of CERN. The pale blue countries are associate members of CERN that include Pakistan and Turkey. And the green countries are observer countries like the US and Russia. And the red countries are other collaborating countries. So for some years now, we've been welcoming Palestinian students every summer to CERN. there have been, still are, several PhD students working on Atlas, and there is one who recently graduated who is here in this room. Ahmed, where are you? There's Ahmed. Okay. Now return to Al-Najah National University. There's also postdoctoral researchers working at CERN. I'd also like to pay tribute to the International Center for Theoretical Physics in Trieste, which has been active in providing courses and supporting Palestinian students to collaborate with CERN. And Kate, could you just wave your hand? So Kate there spent several months at Birzeit University working with Palestinian students to help learn about particle physics. I'm on the board of the Sharing Knowledge Foundation, which has an agreement with CERN to support Palestinian students. And I'm glad to say that this past week, while here for the Advanced Palestinian Physics School, we were able to select a next Palestinian student to study physics, working on experiments at CERN. And I'm also very glad that back in December, we signed an international collaboration agreement between the Palestinian government and CERN. We are happy to work with Palestinian physicists the same way that we would work with physicists from any other country. Shukran.
We thank Dr. Alice, and we have some time for very few questions. If we can have the lights, please. Daw. Okay, so we'll have some questions. Please raise your hand. I can't really see very well.
So I can see one right at the back there.
Okay. Let's start with John Weiner, and then we'll go to the back. We will have a few questions only. John?
My question is, in your list of 7 things that go beyond the standard model, you said that supersymmetry could explain 6 of them. And the one that you left out was neutrino mass. And I'm wondering what it is, why that is true. And now it's too late. I already answered the question.
So we have ideas about where neutrinos might acquire their mass, but they don't require supersymmetry. They're not incompatible with supersymmetry. You could combine the two, and that would have interesting experimental consequences. But neutrino masses, you can get them without invoking supersymmetry.
Dr. Uthman Zalloum from Polytechnic.
The first question is, how could Higgs boson gives a mass in a real life situation? Number 2, now in one of the slides you mentioned that the photon is massless. How could that agree with Einstein relationship? E equals mc squared.
Okay, so maybe I'll start with the answer to that question.
Thank you.
So E equals mc squared is a non-relativistic limit. If you consider a particle with non-zero mass, then its energy is related to the mass and the momentum by E is equal to p squared plus m squared. I'm forgetting about the factors of the velocity of light.
C is equals to 1.
Yeah. So if the momentum p is equal to 0, then E is equal to m. And that is the famous equation E equals mc squared when I put the factors of the velocity of light back in again. But in general, the energy is bigger than m, and the difference is what you would call the kinetic energy. Now, if you consider the limit where p is much, much bigger than m, then E is essentially the same as p. And the photon, that's a particle with 0 mass, so E is always equal to p. And that's completely compatible with special relativity. Now, with regard to your first question, so the point is that any particle propagating through the Higgs field that interacts with that Higgs field acquires a mass. Its dispersion relation is modified by the interaction with that background field in the same way that, say, a particle going through a plasma acquires a non-trivial plasmon mass.
Any other questions? Dr. Hassan Hanaishi.
Right. Yeah, well, thank you. So what actually my student and I did was a fit where we didn't assume it was linear, we allowed it to be a power law. And what we found was that the power was completely compatible with linear, with an uncertainty of about 0.02. Okay. Now, I think actually if one did the analysis now with more data, one would get even higher precision. Somebody should do it to check whether it's still compatible with a linear power. But we did check that.
Thank you, Professor Ellis. Due to time constraints, we have to move on. Let's thank him again. Now we need to move to the Faculty of Allied Health Sciences, and it's going to be through that door to the building on your left-hand side once you go downhill. Not very different from the Mexican hat model. So we'll see you over there at the Faculty of Allied Health Sciences in a few minutes. Physics will be in room 101, and math will be in room 006.
خرف مساحة ولا لا لا بعطيك خليها سكر الباب طبعا بتخرفوا برا اتفضلوا يلا زيد الباب انا اللي برا برا جوا جوا Okay, welcome again. We will start the second session with the first invited speaker, Professor Dr. Atif Kasrawi from Arab American University. Welcome, Dr. Atif. You have 20 minutes. And
Thank you. Thank you very much for giving me this opportunity. I'm so happy to be with you. And at first, excuse me for my bad sound because I'm a bit ill. Today, I will talk with you about the physical design and dynamic analysis of the resonant anti-resonant optoelectronic microwave devices. Concurrently, we are suffering from the problems of keeping technology up to date. You know, semiconductors is 100 years old science, and finding something new, something effective in that sector is very hard. Nowadays, we are, converting everything into nanotechnology, and keeping in microtechnology or in the use technology is a bit hard and is a very suffering problem. For this reason, nowadays, science is going to combine device together. For example, one device may handle 4 or 5 duties together instead of one as used to be. Here in this work, we have tried to design a multifunctional optoelectronic device that can carry more than duty at one time. These designs need the combination of hybrid device layers to give rise to one novel functionality. Example of this, multifunctional three-dimensional switches like transistor, that can carry many cycles of memory storage, need many layers together. Magnesium oxide is a famous material in this science. It exhibits negative resistance and negative capacitance. These two instrumental elements reduces the voltage drops through electronic circuits and thus reduce energy. From this point of view, we attempted to design a new device. The features of our multifunctional device is actually we tried to use the gallium selenide thin films because it has infrared nonlinear optical properties, and it has photoelectric property as analyzer of polarized light. On the other hand, metal gallium selenide interface is published to have conduction by tunneling transport, and it has photoresponsivity of around 5,000 amperes per watt. This is extremely high ratio, which can rarely found in literature. After that, we also check the responsivity time, because the responsivity time will control the amount of data transfer in a second. It is around 1 to 20 milliseconds. The magnesium oxide has a very wide energy band gap, which is 7.8 electron volt. This will behave as an optical window to the magnesium layer. Now, the first test is what is the crystalline nature of the gallium selenide. We find that it is amorphous nature, and when you take the scanning electron microscopy, you obtain regular grains that could not continue together. So there are random or fluctuation of continuous grains. The irregular orientations of the grains assure the amorphous nature of the gallium selenide. And at the same time, we look at the magnesium oxide. Magnesium oxide, unfortunately, evaporate at around 2,700 degrees, and it cannot be used in laboratories as thin film layer. So it must be chemically treated. Treating this chemically, it was solved in a binder composed of sodium based. The X-ray diffraction here show that it is a cubic structure, and it also contains the hexagonal nature of Na2 or sodium dioxide. The scanning electron microscopy show well crystalline grains of around 200 nanometers. So we are dealing with an amorphous substrate, built under an bubble crystalline substrate, and there is cubic structure mixed with hexagonal structure. Okay, we dreamed in this to have different optical properties. Immediate check of the transmittivity showed that the gallium selenide is highly transparent and near the band gap, which is around 2.1 electron volt. Okay, it reached maximum transparency beyond that point. Similarly, if you look at the magnesium oxide, even though you are in the visible region, still the magnesium oxide is transparent of just only 50%. And if we immediately look at the double layer, when you construct together, you find that there is a significant shift in the transparency. Consistently, I immediately look at the reflectance because there is no time for discuss these. You will see that there are two peaks which may be assigned to the plasmonic interactions. Combining these two layers together give you a moderate reflectivity. And if you look from the energy point of photon energy point of view, you obtain that the double layer magnesium oxide gallium selenide double layer enhance the absorbability up to 60%. This means that whatever the energy value is, infrared or UV visible, or even if you exceed up to ultraviolet, this material will be capable to absorb some light. If you calculate the energy band gap using Tauch equation, you find that the gallium selenide is 2.1 electron volt, and when you make the double layer, although we are expecting the magnesium oxide not to affect the energy band gap, okay, it is shifted to 1.9. However, our dream is not to have this value because the difference is only 0.2 electron volts. To establish any optoelectronic device that can handle more than one functional tutor, you at least need 0.7 or 0.6 electron volt difference to prevent leakage currents or internal shorts between the two valence bands. For this reason, we first search for the reasons of this low energy. We find that the lattice mismatch is one reason, okay, and the interface charge dipoles is another reason. The electron hole recombination at the depletion layer boundaries could be another reason for this difference. Applicable, when we check the applicability of this device, we find that the valence band shift is 0.2 is insufficient, as I told you just before, to create thin film transistor. And this to have this device, you must have a strong carrier confinement with the valence band, and it should be large in order to avoid the high leakage currents. With this value, the 0.2 electron volt, it is suitable for quantum dots. But our purpose is not to have quantum dot. Our purpose is to have many functional device, not one purpose device. For this reason, we have redesigned the device. We constructed another device based on this fact. In the new design, we evaporated the gallium selenide on aluminum, and we covered it with magnesium oxide. The magnesium oxide is covered with silver again. Actually, the silver and aluminum approximately have the same work functions. There should be no difference in using which one of these. But the silver make stronger contacts because its electronic configuration is higher than that of aluminum with the magnesium oxide. That's the reason why it was preferred on the top of the magnesium oxide. The both layers, of course, gallium selenide is N type and magnesium oxide is B type. When we calculate, we tried to construct the band diagram for this device. We recall the electron affinity values of the gallium selenide and the metal work function of aluminum. So you have at first on the down shoulder aluminum gallium selenide Schottky diode. You go up, you find B-N junction. Sorry. Okay. And when you look at the same time at the magnesium oxide layer, you will find a barrier height of 5.76. Because this is B type, you must find a metal which have higher metallic function than this value. This is impossible. Only platinum can make ohmic contact with magnesium oxide. For this reason, whatever you use, you will obtain Schottky device. So in the total area we are working, which is actually this is micrometer, I am sorry, it is a wrong display. Okay, in a 2 micrometer region, you have Schottky, B-N junction, and another Schottky. Some computational calculations are needed to optimize the real value of the valence band, because before subjecting to electricity, if you didn't fix the value of the valence band shift, the device will burn. This is very dangerous. For this reason, we fixed the offset of the conduction band as 2.38, and we have carried out a computer analysis to find the shift in the valence band, which is 2.89 after computational analysis of the binning parameter. Now, in accordance with this value, this device should suit any type of application, but this is theoretical. The design band diagram is also shown here. As you can see, we have we have 3 layers. One layer is for AG, the other is for magnesium oxide, gallium cyanide, and the other metal. When you look at the design of the device, you have 4 type of barriers. One is here, followed by another, followed by another. Then these 2 narrow barriers should be the tunneling barriers. That's what we are dreaming to use actually. We are not interested in the BN junction contact because it is typical. It is typical diode. We want a tunneling barrier because the tunneling barrier means the barrier which carry information through communication. The signal information analysis need tunneling barriers in order to separate signals from each other. The operational principle of this device is simply we have 2 diodes. We give the depletion width for the first diode as WD1 and the other for WD2. And if you add both, it will complete your diode. The MSM device now is composed from 2 back-to-back Schottky diodes connected to a BN junction in an area of 2 micrometer. Now the dominant current in the device should be 3 currents now, even though I'm talking theoretical still. I didn't apply. Okay? The forward saturation current, generation recombination current, service leakage current. I want to look at these 3 first. The forward saturation current, it is a typical diode behavior. That's what we want. We don't want the current to pass from one way and not from the other in order to carry a logic in dealing with this device. The generation recombination, if I want to use it as a solar cell, I need high generation recombination ratios or recombination centers to have high currents in a low open circuit voltage. The service leakage current is actually the current which refree the plasmons, that is, which separate the information from the original signal. These 3 currents are necessary to exist in such electronic device. Of course, there are parameters that must be evaluated. The reach-through position, that is, when you connect one Schottky, the other will be reverse pairs. So one barrier is narrowing, the other is widening. At one instant, one of the diodes will reach the limit of the other. So this point is actually the point where the diode will burn. So we must fix this. In our calculations, we have demonstrated it through IV characteristics. Now the design is real and done in the laboratory, and it is applied. If you look at the forward direction, which is given from the aluminum gallium cyanide side, from bottom to the top, you will find that the current is less than 20 nanoampere, while when you look at the reverse direction, you will find it is around 200 nanoamperes. When you try to analyze these in accordance to Boole-Frankel and Richardson-Schottky analysis, you find that this is actually a tunneling barrier. The tunneling barrier here is necessarily indicate that the current is proportional with the exponent of the square root of the voltage. When we do this analysis, we find 2 barrier heights. While forward bias you have 0.82 and reverse 0.81, but the difference is in the depletion layer. The forward one is 670, that's why the current is low, and the reverse one is 116 nanometers through reverse bias. Looking at the conduction mechanism of the device and calculating the flat band and reach through depletion width, we are in a trouble with defining the built-in voltage. For this reason, we have calculated the capacitance voltage characteristics, which are shown in the inset of this figure. From this value, you find the built-in voltage 2.1 volt. This leads to a flat band voltage of 163 volts. So, if this device is used on a board, and the board is subjected to a shock, and the shock never exceeds 160 volts, nothing will happen to this device. It will still be operating. Similarly, if you look at the reach-through, where it now stop performing well, okay, it will stop performing well at 126 volts. That's what we want it to have, because 0.2 volt was very dangerous for using it. Now, we look at the depletion width of the first device. You find it as during the forward bias, you find the flat band is 18 volt and the reach through is 5.89 volts. Oppositely, on the reverse bars, it is 116, and the flat band voltage is 0.55, and the reach through is 0.25. Now, the dynamics of this IV characteristics is actually listed in front of you. When the positive current is provided from the aluminum side, the PN junction is reverse bias. The holes in the magnesium oxide are pulled away from the depletion region to the gallium cyanide magnesium oxide interface. Electrons in gallium cyanide will also be pulled away. So the depletion will widen. Because they are far from each other, you obtain 670 nanometers. On the other hand, the holes in the magnesium oxide are pushed toward the AG metal. This increases the voltage barrier, causing a high resistance to the flow of current. That is why the current is still low during the forward biasing of the device here. Sorry, in this part here, in the top of the figure. Oppositely, when you go to the other side, the reverse bias, the positive voltage is supplied from the AG metal, and this is the depletion width is now defined by the difference between the two voltages. The application of V decreases the potential barrier for the electrons moving, and as the PN junction is forward bias, the electrons in the N-type gallium cyanide layer, which have been elevated to the conduction band, and which have diffused across the junction, find themselves at higher energy than the holes in the beta. This is the tunneling region. This is the important here. Now electrons can tunnel easily at this edge. They are combined with holes of the making a continuous current flow, and the barrier width is 116. We have tried to apply this. This is interesting. We have a machine that can input 1 megahertz up to 1,800 megahertz with a biasing voltage from 0 up to 40 volt, positive, negative. This is an impedance analyzer in which you can evaluate any waveform you inserted. We have inserted from 1 megahertz up to 1.8 megahertz and recorded the capacitance, resistance, impedance, and the quality factor of the device. If you look at the module side, you see that unbiased signal, which is known in the mobiles as Bluetooth. Okay, Bluetooth means unbiased, 0.2 volt approximately, or 0 dBm, unbiased. Okay, you obtain that this device starts responding at 1 gigahertz. 1 gigahertz is a relatively high ratio. If you set a biasing of 5 volts, this resonance anti-resonance condition, shifts to around 6 megahertz. The blue colored in the figure. Now, another interesting property is that the capacitance itself is negative. It means that if you insert this element in a capacitive circuit, it will start cancellating the capacitance at 1 gigahertz if this is a Bluetooth. Okay, that means if there is a memory stored data, it will be recalled again at 1 gigahertz. Okay, by cancellation. So it is converted to, instead of capacitance, it is single. Similarly, for the resistance, you obtain the same idea. Now, the negative capacitance widen from 1.03 to 6 to 1.2, from 6 to 1.8 when you raise the biasing voltage to 5 volts. So the biasing is a very good controller for the memory recall. Where to respond, what to do this device, depend on the applied voltage. If you think from 0 to 5 volts as a limit of any board, this is a very, very, very wide range of control. So it can carry many duties at one instant in that region. The negative capacitance for us, okay, is caused by the injection of minority carriers. As I told you, they reach the conduction band. From there, they tunnel. Okay, when the device is forward biased, and it is actually change the signal properties. It change the signal properties of the resonant electronic circuit, like the ambient sensor interface, to control the oscillation of enhanced tuning. Okay, it also can be used to increase the tuning range of the voltage controlled oscillations at 1 gigahertz and 6 megahertz. Z is equal to R. There is a resonance anti-resonance phenomena in that one difference between the resonance and anti-resonance is 70 megahertz and 10 megahertz under 5 volts. This indicates that the number of data transfer cycles could reach 70 millions per second. In other words, it is 280 millions bits per second. Or in the language you are using, you can download 1 gigabyte file in 25 seconds with this device. Of course, the important in this device is its size. It is 2 micrometer device. It is not a large mobile you are using in your hand. It is very, very narrow one. And similarly, of course, this make it attractive for communications. I am sorry. We have a simple problem. Our problem is actually the magnesium oxide content alters the optical properties, and this leads to dielectric breakdown at some particular electric fields. For this reason, research must continue in order to fix this problem. Unfortunately, this needs chemists which can control the content of magnesium oxide without altering the energy band gap. Okay. Finally, I would like to say that this project was published in the Journal of Electronic Materials, IEEE journal, and was awarded by Zuhair Al-Hijjawi Award for Ms. Renal Ikmail last year. Thank you very much.
Thank you very much, Dr. Atif. Any questions, please?
I'm a little bit confused, but what physically mean a negative capacitor?
Uh,
We know simply what a positive capacitor do, and we always teach that a capacitor has a positive value. What does a negative capacitor is?
Negative capacitor means that in its original value, without dynamical analysis, without the insertion of AC signal, it have a C0. Okay, capacitance C0 say. When you insert a signal, the capacitance start decreasing. So it is actually a differential capacitor compared to the original value. For example, the capacitance is 20 nanofarad. It become 18, 16, 14, 13, 12. So it is negative with respect to the original value. Is it okay? No. The capacitance, the negative capacitance is to cancel the charge. It is a baristic cancellation. Its duty is this. Okay? With some modifications, simple modification, not much. Okay, you will need to include the impurity levels in A and in D and in I, intrinsic impurity levels, to have its original value. It is actually differential, not fixed as we are thinking Q over V or no. You need to consider differentials. Yes.
Okay. Any questions?
You said that you have put an AG layer to increase the band gap. Now, what you have AL layer, then MGO, then lastly the AG layer.
AG layer not to increase the band gap. AG layer to create another barrier. Okay, we have thin barrier. The thin barrier will make short, but the setting of the AG layer will forbid the current from reaching the mid because it is reverse biased. Okay.
Because it's a good conductor, yes.
Yeah, yes.
Just a random question. What's
Yes.
the growth method of the magnesium oxide substrate? And have you tried working with crystalline substrates?
Yeah. Magnesium oxide is already a crystal powder. Okay. It is melted in sodium-based silicate. Okay. Because it is you cannot evaporate it in the laboratory. You have to convert it into paint, okay? So that's the process. But even if you convert it to paint, it does not lose its crystalline nature, okay? You can think that you have a hexagonal box containing cubic boxes. There is no problem in that. The case is, what we are suffering from or we are trying to solve is actually, okay, how to keep the energy gap from this shift. It seems that some of the valence electrons that are coming from the binder are affecting the magnesium oxide. That's a problem. Okay.
Any questions? Thanks again, dear Dr. Atif.
Thank you very much.
Okay, the next invited speaker is Professor Dr. Muhammad Abu Samra from Arab American University and the Dean of Faculty of Sciences. Welcome, Dr. Muhammad.
Good evening, everybody, and welcome to our conference here today. I will talk about the diffusion coefficient of vacancies and jump length of electrons in Mg ferrite. We don't need this. Okay. Actually, the ferrite system, as any other compounds or any other materials, sometimes used in technical or in electrical components of communication, chips, computer parts, etc., etc. And MgFeCrO2 ferrite is used generally to have an electronic devices in microwave regions, and it has some good conduction. Now the problem is we have, for instance, the ferrite, the iron has, for instance, two systems. One is the FeR plus 2 and FR plus 3. The FeR plus 2 is sitting on a basis of a crystal which has a tetrahedral shape, while the FR plus 3 system is sitting on an octagonal system. Now, most of the electrical, mechanical, optical properties for this ferrite has been already done. What we have here is just to study the diffusion coefficient for when the ferrite is moving from or transporting from tetrahedral to octant lattices or something like that. So first of all, we want to talk, if we talk about the fusion, which refers to some moving of some ions or atoms or whatever the molecules from one side to another. If you have a powder, two sectors or two sections, so the molecules can penetrate or can move from side to another side. And you can, for instance, if you look here, this is the changing in color here, means that molecules can move to and fro from both sides. Actually, the same thing here, according to Fick's first law and second law, we can apply these things in order to get the diffusion coefficient. Now, if we have, for instance, as I mentioned here, we have to study the ferrite or the iron movement, and the preparation of such a system or such a compound is similar or can be used with the ceramic methods, in which case the material or the raw materials are crushed by machines or by whatever it is, and they, for instance, they combine with each other, and they are making pellets with some dimensions, and they prepare the measurements. Now we have here, if we use, for instance, if we want to study the diffusion coefficient on the dependence on, for instance, the transfer, the temperature or whatever it is, using this equation here. Here is the equation sigma, which is the conductivity, DC conductivity in the number of electrons or number of carriers, either charge of electron, the diffusion coefficient, KB Boltzmann factor, or T is the temperature, and the concentration X here would depends, its value is taken from 0 up to 0.9 or maximum 1, because we don't need any other concentration above that. If we, for instance, measure using the measurement, the diffusion coefficient, using, first of all, we have to measure the DC conductivity. From that, we have to, for instance, use the equation in order to get D. If we calculate the diffusion coefficient, and, for instance, with, and we took the logarithmic scale, log D versus the temperature over or 1 over T, we found, for instance, the diffusion coefficient or the factor is decreasing by increasing the temperature. So in that case, that means when we have, for instance, more energy, that the vacancies or the ions or whatever, they can diffuse from one part to another and they can change their positions. The second thing here, this is the, for instance, if we take, for instance, the, okay, الآن, as I said here, we have a noticeable increased diffusion coefficient with increasing temperature. As we now, the oxygen vacancies have been reported, reported to accelerate diffusion and central process. We have, for instance, oxygen vacancies or atoms or sites that if it's present, then it will accelerate the jumping or moving the FR sentence. Now, the diffusion, if the diffusion of oxygen vacancy decreases as chrome ion concentration increases. This is the results. Now, the migration of Fe+3 ions to replace Mg+ at tetrahedral sites due to a substitution of Cr3 instead of Fe+R at the octahedral site might cause the formation of cation vacancies, and for higher concentration of Cr. This is increasing the concentration of the chrome, and the LUTs vacancies are occupied by cations, and for cation vacancies increased which reduce the diffusion of oxygen. That means if we can increase the scattering or the movement, then the vacancies of oxygen will be reduced, or maybe it might be occupied by other cations or ions of Cr+3. The dependence of the diffusion of the coefficient of diffusion temperature, we found it depends on the exponentially decreasing with temperature, as it's here, which reflects here the equation or the dependence here. Here, if we take the logarithmic of that equation, we will get, this is in agreement with the equation derived by others here, the equation. Now, if we, for instance, the broken lines at a certain critical temperature, we have here at the here at some times we have a constant value. That means we have some changes in phases, and Tc here, it means Tc, we have, this is called Curie temperature, in which the material can transfer from para to paramagnetic to ferromagnetic, or to here is the Tc here, where the temperature, where the less temperature decreases, for content increase, if they have increased. Now also that the Curie temperature or the critical temperature is called the Curie temperature, the ferromagnetic material transfer to a paramagnetic in this stage here. Now, okay. We have also the activation energy for the diffusion process in the paramagnetic region here in this figure 1. Okay. In a maybe not here. Here, the Curie temperature with the concentration. If you increase the concentration, that means the Curie temperature decreases. In both cases, here in this case, that the transformation or the transformation of the material or the compound from, for instance, ferromagnetic to paramagnetic, that means its magnetic properties will be decreases or decreasing by increasing the concentration. As you increase the concentration, then the magnetic properties of the material is changed. Here, the energy the activation energy with the concentration. The activation energy will increase by increasing the concentration. Even we have, for instance, the if you increase the temperature or increase the concentration. Now, if we take, for instance, the jump length, when the ions or the for instance, Cr+3 jumps from one side to another or from one lattice to another, the jump limit can be, of course, the lattice parameters are found or calculated or assessed by using the X-ray diffractometer, and that's the shape, or for instance, the crystal type is known by using such a diffractometer. The jump length is calculated according to the equation here, where L is the jump length, A the lattice parameters, and of course the ferrite here, the structure, the crystalline structure of the ferrite, always it's a cubical system or a cubic crystal. That means we have A is the side of the cube or the cubic lattice. If you, for instance, if you plot L, this is the conduction DC conductivity versus the concentration. If you increase the concentration, then the DC conductivity decreases to a certain value, maybe to 0. Then the jump length, this is here the jump rate. It's defined at D over A squared. D, the diffusion coefficient, A square is the square of the lattice parameter. If you have here if you go to some properties, if you increase the diffusion during the centering and decrease the density, the CR addition decrease the density. If you add Cr+3, then the density of the ions will decrease, which is explained by the basis that CR3 has a smaller atomic weight than that of Mg+2, and that we have, for instance, penetration of these ions, or they form or they cluster at a smaller distance. Now, for instance, this is the diffusion coefficient with X, because concentration. The diffusion coefficient also is found to decrease with increasing the concentration, and also the density of the ions also is found to decrease with increasing the concentration. Here, the atomic, for instance, if you want to calculate the atomic radius or the atomic the thermal radius, it can be calculated use this one here, where RA is the radius of the smaller ion, or R capital is the larger, which is Cr3 or Cr+2. Okay, this is, for instance, here also, this is the conductivity or the A, the atomic parameter or lattice parameter as a function of concentration. It's found that the lattice parameter decreases with increasing the concentration. That means the material or the lattice, it can be filled with other ions or other compound, and that means the diffusion becomes slow and slow or less than. The here's we talk about this one, and here is the, for instance, the radius of the ions. If you increase the concentration, that means the atomic radius and the ionic radius. If you increase that, then some of them, the ionic radius decrease by, while the RB, the anion radius will increase. That means we have a space for the two atoms to cope or to adjust with each other. Also here, we found from the analysis of the fusion and activation energy, the fusion process determined in our study here, we conclude that the studied sample of the oxygen atoms diffuse through structural vacancies rather than thermal equilibrium vacancies. From the X-ray analysis, we can give suggestion of cation distribution than the simple jumping. Then by adjusting the theoretical less parameter will be equal. And here, okay, this is the references or whatever. Thank you.
Thank you very much. Any questions? No questions? Oh, thank you very much, Dr.
You're welcome.
Next speaker, we have Dr. Karam Awawdi from Palestine Technical University, Khaduri. Welcome.
Okay, good evening. The main title of my talk, Compact Modeling of Contact Effects in Organic Thin Film Transistors. We work in a group, large group. We have 5 teams in this group. And the outline, contact effects, model for output characteristics, drain current, drain voltage source, incorporations of the contact model and parameter extraction method, our method and test results and conclusion. Now, the organic thin film transistor has many problems, and the one of them, the contact effect. The main challenge here to propose a good model and 2 integral in DC and thin film transistor, and also to propose a method to extract parameters appear in a model. Now, the contact effects, as we seen in this schematic diagram, we see in a contact region with low conductivity. And some experimental observations, like surface micrographs, we see the grains, the change of the size in grains when we approach to the interface. Also, by using scanning potentiometry, and this result taken from this reference, we can see 3 things in this result. The voltage drop split between contact region and intrinsic channel. And the second thing, the voltage drop in contact, especially in injection charge. And we can distinguish between ohmic or non-ohmic to more ohmic relation. Now, model for output characteristics, and we will talk about generic charge drift model. This model was proposed by authors in the first reference. These authors introduced the contact effect in organic transistor, or introduced the contact effect in generic charge drift model. And
we proposed the contact region, and we introduced also the formula of the contact region depends on the behavior of the current in the contact. If the behavior of the current in the contact linearly, this meaning we can use Ohm's law. If the behavior of the drain current in the contact region quadratic, we can use Mott-Gurney equation. Now, also the authors of generic drift model uses this method to extract the parameters. And this method or this technique is called HVG function, and is equal the integral drain current divided by drain current. And this technique depends on two regions, saturation and linear region. We use the same technique and we use the same generic drift model. But firstly, we want to talk about the effect of neglecting contact voltage to the determinations the threshold voltage. We use theoretical values of transistor. Gamma is equal 1, threshold voltage is equal 4.5 volts, and contact voltage is equal I multiplying by R. And we suppose here the behavior is linear behavior. Now, from this figure, we can see the threshold voltage in the range 4.5, but with greater value of resistance, we can see the threshold value go to the other range. And we use the same parameters to know the effect of neglecting contact voltage in the determinations of gamma. Now the value of gamma is equal 1. We can see the value of gamma in this region is equal 1, but with greater value of R, we see the gamma goes to other range or in negative value. Okay, now we will talk about our method. We use the same technique. We introduce the contact voltage in the technique, but not in the generic drift model. In the generic drift model, the contact voltage is treatment, but in method to extract the parameter, the authors assumed Vs is equal 0. But here, we introduce the Vs and HVG function, and now we can extract the initial mobility for single transistor with fixed length of channel. But the previous author used another methods to find the initial mobility by using a transistor with different lengths. But here we can extract the initial mobility for the single transistor. Now, we have this experiment data, and we have these parameters width, length, and capacitance, and threshold voltage, gamma, and mu zero. Now, we use the traditional methods to extract the threshold voltage and mu zero by plotting a drain current versus gate voltage. Okay, and we introduce the contact voltage in drain source, but not in gate source. Now, we change the M parameter to get a good fitting between experiment and theoretical values. Theoretical values, solid lines, and experiment values across or star lines or dashed lines. Now, in first trial, we have a threshold voltage minus 3.4. But the original data, we have threshold voltage minus 2.5. Gamma 0 here, without value of gamma, and the mobility is less than the or greater less than the mobility in the original data. Now, we use HVG function to extract the new value of threshold voltage, and the new value of threshold voltage is minus 2.52, and gamma is minus 0.14. We can find these values from the black solid lines. From saturation region, slope is equal 0.32, and the intercept is equal minus 1.52. By using new value of threshold voltage and the new value of gamma, we get a good fitting between theoretical and experimental. But when we plotting drain current versus contact voltage, we see the slope of curve turn with clockwise direction. And this very strange, because must be the slope increasing with increasing contact voltage. This means we want to change or to select another value of gamma. We select this value for gamma, positive value, and we change the M parameters to get a good fitting between experimental values and theoretical values. When we plotting drain current versus contact voltage, also we get another strange case, and the slope turn a counterclockwise direction. In this case, we change the gamma value to 0, and we get a good fitting and slope increasing with increasing contact voltage with the new values of parameters. Now, we want to test my method by using this transistor, and we get a good fitting and with a good values of threshold voltage and gamma, and with M parameter values. This means we have a method with contact voltage to extract the parameters of the generic drift model, and conclusions we have proposed a model to characterize the voltage drop at the contacts of organic thin film transistor. This model has been introduced in a generic compact model to describe the output characteristics of the transistors. A procedure to extract the parameters of the model has also been proposed. We have tested the characterization method in transistors with known parameters, obtaining no significant errors between the rear parameters and the final trials. Okay.
Thank you very much, Dr. Karam. Any questions?
Thank you very much for your presentation. It was very kind and interesting. I am wondering about the value of the mobility. The mobility is of the order of 10 to minus 7, which is very, very, very low for thin film transistors or for transistors engineered to be used. You know, the mobility represents the concentration of electric field in the transistor. With this value, I don't know, is it an input or is it a measured value?
This mu 0 mu zero.
Yes.
This is the initial value of probability. But we have another equation to calculate the final mobility. Where is it?
Yeah, I am wondering why do you accept it as an acceptable value? It is very low.
Yeah, M0, very low. But we need, where is the equation, to introduce this value, the initial value, in another equations with gate voltage and threshold voltage to calculate another value of mobility. But this is the initial value of mobility, mu zero. Here is the initial value of the mobility.
I am sorry.
No, yes.
I took much time, but what is the highest mobility that you reach in your calculations?
Here, I haven't exactly arranged for the mobility, but from calculation and by using data from literature and by using my methods to analyze that data, we get the same reading.
Okay.
And this mu zero for this data from literature is equal multiplying 10 to the power minus 7.
Yeah.
This is value, the original value in the article in the literature. But
I see.
Yeah.
I don't want to stop much on this value, but I want to ask another question, please. What do you expect the lifetime for this organic thin film transistor to last? How do you expect its lifetime? Do you expect it to work for a long period because it's organic and subject to heating and cooling?
I'm not working this field and to check the time or the lifetime of the transistor, but we proposed a method to.
Yeah, I understand.
Yeah.
Just I am trying to learning from you if you know this. I know what did you work. Thank you very much.
Okay, thank you.
Any questions? Okay, thanks again, Dr. Karam. Next presentation, Dr. Riyad Sa'aduddin from Al-Najah National University. Welcome.
Good evening, everybody. I am very pleased to be between you to present our research work. Today, my presentation, I will talk about tungsten oxide thin film, non-crystalline one, doped with different atomic concentration of titanium. Tungsten oxide is well known to be one of the most popular transition metal oxides, and in its nanostructure materials, they have received recently great attention due to their potential application like gas sensors, photocatalysts, electrogaso, and photochromism. This variety of optical and electrical properties is due to the features that tungsten oxide film have. It is a wide band gap semiconductor, about 2.7 to 3.2 electron volt, and it has 5 different structures depending on preparation temperature and conditions. Also, in its porous form, it is found to be excellent in sensing functions, and when it is amorphous, it's suitable for optical and electrical sensors. Our objectives in this work is to study the effect of titanium doping to such tungsten oxide films. We will study the structural properties by XRD measurements. Also, we will have the optical parameters like energy gap thickness, coefficient, absorption coefficient from optical measurements, transparency and reflectivity. Moreover, we have studied some oscillator parameters corresponding to energy less than the energy band gap. Preparation of our film was done by dipping glass substrate into prepared sol gel, like shown in this photo. The sol gel was prepared by mixing tungsten hexachloride and titanium dichloride in a solution containing ethanol and lactic glucoside, which was kept to react in ultrasonic vibrator for about 2 hours to have dark blue color. After dipping the film, it was heated at such low temperature, 160 degree, for about 2 hours to have transparent tungsten oxide films. For the result, from this shown figure, all films with different titanium concentrations show same XRD diagram like the glass one. You know, the glass substrate is put as a reference here. So with no additional peaks correspond to tungsten or titanium, this means these films have amorphous nature. Indeed, this is well known because tungsten oxide films crystallize at 350 degree or higher, so it must be amorphous. Other experiments done on this film, which is the transparency, as you can see, all films show a systematic increase of transparency with lambda, with transparency exceed 40% for lambdas above 550 nano. Okay, this relative high transparency is due to the wide energy gap of tungsten oxide, which is about 3 electron volt. From this data, we deduce the absorption coefficient curve versus the incident photon energy. And we can see for different titanium concentration, as titanium increase, the absorption coefficient decrease. This decrease is due to the increase of the film, maybe, and second reason, it is maybe due to the existence of titanium compound reflecting centers in the film. So the absorption will decrease and the reflection is expected to increase for these films when doped with titanium. Absorption coefficient together with incident energy are used to calculate the energy band gap using this famous equation with eta equal half for allowed direct allowed transition. We can draw alpha H mu versus H mu like shown in these curves and extrapolate the linear part of the curve to find the energy band gap from this intercept with the energy axis. So the energy band gap was found initially from 0 to 10% of titanium to decrease as shown in this figure. Okay, this decrease in this figure is maybe due to existence of titanium dioxide clusters, small clusters within the film. You know, for low number of clusters or small clusters of order 1 or 2, we have energy gap which is low, 2 electron volt or 2.9 sometimes. And also electron affinities lower than that for tungsten oxide, which means that titanium may substitute tungsten in the tungsten oxide film, and hence the energy gap reduced according to this substitution. On the other hand, for higher titanium concentration from 10 to 40%, we have seen that the energy gap increase, which is due when having larger cluster of titanium oxide, we have energy gap which is higher than or in the order of tungsten oxide, which lead to increase in the energy band gap. Other experiments have been done, which is the reflectivity. As shown in this upper figure, we have a reflectivity of weak order, of weak ranges from 0 to almost only 4.5%. And as expected from by alpha, we have the reflectivity increase as increasing titanium when the titanium concentration ranges from 10 to 40%. This is due to existence of reflectivity centers and from titanium dioxide, and also film thickness, which is increased with titanium, as we will see later on. However, for concentration from 0 to 10%, the reflectivity decrease, as we can see here, which is due to the lower energy band gap observed for 10% of titanium. The film thickness used in the past calculations was deduced from reflectivity measurements, from the interference pattern in the reflectivity measurements, from which we use this equation to find the film thickness. And we have found that as titanium increase in our film, the thickness increase up to a constant average value of 730 nanometer, which is due to the increase in the viscosity of the sol gel when adding titanium to it. Also, from reflectivity measurements, we have calculated the dielectric constant, the relative one, using Fresnel's equation of series unpolarized light, from which our reflectivity measurements represent Rs plus Rb over 2. And taking our experimental conditions into consideration with some algebra, we can deduce the dielectric constant equation with Rs equal to this one, where the reflectivity is shown in this term, which is our measurements. We put it just here and substitute here to have the dielectric constant, which is shown for different films at different wavelengths. In this figure, you know, as titanium increase, we have increase in the dielectric constant due to the formation of titanium dioxide insulating phase in the film. And also you can see that as lambda increase, the dielectric constant increase, which is again due to the increase in the reflectivity while increasing the it's not again, this is the first time, you know, reflectivity was found to increase with increasing lambda, so E will increase due to that. Other parameters have been found for our films, like dispersion energy, oscillator energy, static dielectric constant, and lattice dielectric constant. It will be shown in the next one. You know, in these calculations, we have used the single oscillator model by Wimble and Dido. From this equation, we just draw 1 over n square minus 1, where n square is the dispersive refractive index, and versus energy or photon energy square, and the energy is in the range lower than the energy band gap. Making this drawing, you know, this is an example for only one concentration of 40%. We can have the slope and the intercept, and from the previous equation, we can see the slope equal to 1 over ED E node, ED dispersion, and E node is oscillator energies, and the intercept equal E node over ED. So we can deduce these two values from this slope and intercept. Static and lattice dielectric constant are found, you know, static dielectric constant can be found from the same equation used before by putting energy of the incident photon equal 0. So it's at 0 energy, at 0 wavelength. So you will have a static dielectric constant equal to 1 plus ED over E naught. And using the second equation shown here, drawing n square versus lambda square, we can have the lattice dielectric constant from the intercept. This is an example just for 40%. Others are drawn elsewhere. Okay, in summary, for the oscillator parameters, we have deduced we have oscillator energy, first or second column with different titanium concentration. Dispersion energy, as you can see, these two, E node and ED, has energies in all UV ranges, from vacuum UV to near visible UV, which means all films are suitable to be UV sensors. But however, for samples doped with 10% of titanium, we have the highest value of this energy, which means it is considered to be the best sensor. For the static dielectric constant, we can see all of them have almost same value, which means all film has same dielectric properties. However, for the lattice dielectric constant, only 0 and 10% has almost the same value, which means they have the same structure, which confirms our assumption that titanium substitute tungsten in these films. However, for concentration higher than 10%, we see that the the lattice dielectric constant increases increasing titanium due to the formation of titanium dioxide phase beside tungsten oxide films phase in our film. Just to conclude, we have successfully prepared non-crystallized film doped with different concentration of titanium using sol gel technique, and we have found the best results for our film is when doped with 10% of titanium. It can be used as a UV sensor, plus the well-known application for tungsten oxide as electrochromic system. It must be a good candidate for that. And thank you very much.
Thank you very much, Dr. Iyad. Any questions, please? Any questions? Thanks again. Thank you very much. Actually, we have two lectures from Gaza Strip, but they are not here. Okay, so we'll have a break for 20 minutes.
Slide number 2. Is slide number 2 shown to you? Okay. So, just before I start my talk, I would like to say a quick thing, which is actually to show my solidarity with Ahmad, who was actually one of my friends while a graduate student in the Arab American University, and I took them. Actually, not that I'm showing this, even if not have known him in person. Professor Barouti, as maybe some of you know, has been held without trial and detention since April 24th of this year, and this is actually not the time. It's the second time after another occasion in December 2014, when he also was arrested while trying to support those to Jordan on who attend the conference at the United Arab Emirates. And this is actually a very good example to show how the occupation and dictatorships are pretty much the same. So he was arrested only for posting his opinions on Facebook. So I hope that he gets free soon and he gets back to his family and friends, and also gets back to his research and work and his contribution to the scientific development. So now let's my talk. Beginning, I would like to give you an. So I'm working at CERN in Geneva, Switzerland, an affiliation with French Laboratory and University. CERN give you a glimpse. It's the home for the collider. Thus, an unprecedented center up to 13 will be data. And as you can in the plot, this image is very important because that shows how now in the higher is the cross section of the physics that we're looking at. I'm working at one of the main experiments at the LHC, known as the ALPHAS experiment. And my research had two aspects. Hello? Yes, can you hear me? Yes. Sorry, I noticed I was streaming the video of the lecture. So now I think there is no noise. You hear me alone. So let me continue. If you can hear me. I'm sharing. Okay, just a minute. Let me. Okay, just a minute. You can hear me? Okay. I think the best thing that you go through my slides once I tell you to go to the next slide. So we were talking about slide number 3. Can you please go to slide number 3? You are sharing the slides? نعم نعم سامعك دكتور. But you don't have the slides on your computer? مش عندكم إياهم؟ What? I have sent an email. So something like maybe 15 or 20 minutes ago, maybe more. Yeah, 20 minutes. Okay. Okay, maybe I'll give you a summary. Okay. Okay, let me give you a summary of what I have done. My research has two aspects. The first one was about the Atlas detector studies, and it concluded commissioning of the Atlas pixel detector after we inserted a new layer in the pixel detector in before to start it, while the other part was supersymmetric part, looking for theoretical supersymmetric particles. And as I contributed to the commissioning of the IVL, and the IVL has successfully took part in data taking and success in both years, in 2015, 2016. And actually, I was also part of a physics analysis team in which I have contributed to the signal region optimization study that has to be precede the analysis. And also, I contributed to the fake lepton background estimation using some data-driven methods with the 2016 LHC data. For our analysis, where now we are showing our results in the iChip conference in a few days, unfortunately, we have observed no significant excess over the standard model expectation. So we did not actually catch any supersymmetric particle. But then the SUSY models considered, we set new exclusion limits. Our exclusion limits were extended for 3 different supersymmetric particles, the S-gluino and the neutralino and the S-boson. And as a part of my ongoing studies and future studies, now I'm performing a study to look at the irradiation effects on the pixel detector over a long period of time using some run one data from 2011 and 2012. So this is just a summary. Sorry for this technical issue, and I really would have liked to make a contribution, but it's out of my control.
Thank you very much, Dr. Mahmoud Saidi. If you wish to have it live in next time when in Palestine, we'll be so happy if you make a seminar to our the department team at least. Thank you very much. Thanks, Dr. Mahmoud Saidi.
Okay. Thank you, everybody.
Now we will have Dr. Othman Zalloum. Dr. Othman, welcome to university, please.
Thank you. Today I'll be talking about 3D micromachining of single crystal diamond using femtosecond direct laser writing. I would like to thank Matthew Parrish, Alexander Terikov, and William Hofmeister of the Space Institute in Tennessee. The single crystal diamond samples were furnished by Diamond Edge Company in the United States of America. In this introduction, we investigate the formation of various microstructures in high pressure, high temperature synthetic single crystal diamond by tight focusing 200 femtosecond pulses centered around lambda, the wavelength of 800 nanometer. We made ablated samples of synthetic single crystal diamond, and their replicas, acetate replicas, were analyzed using scanning electron microscopy. One of the key conclusions is that low pulse energy is a key factor for accurate and precise machining of micro patterns. The diamond has unique physical properties that include high hardness and strength, transparency, low friction, low adhesion, high thermal conductivity, low thermal expansion, high refractive index that can reach up to 2.4, chemical inertness, biocompatibility, electrical insulation, and good electronic properties. In 1954, General Electric made the first diamond structure using high pressures from 5 to 6 gigapascal and using temperatures greater than 1000 Kelvin. Of course, diamond is a semiconductor material that has two band gaps. The direct band gap is about 5.49 electron volts, and the indirect band gap is around 7.3 electron volts. And the optical absorption edge is near 253 nanometers. The simplified fabrication workstation for the microstructuring is shown here. We have a microscope assembly. In this picture, we have the microscope head here. We have a beam splitter for aligning beam using visible light. Here we have one of the eye pieces is connected with a CCD camera and to a computer for image grabbing and analysis. The other eye piece can be used for human eye. Here we have the femtosecond pulses, 200 femtosecond, and the wavelength is 800 nanometer, goes into a fully reflecting mirror at 45 degrees, and dichroic mirror, which transmits it to microscope objective to an X, Y, Z nanostage held on an XY micro stage. The assembly is sufficient to explain the concept here. I mean this diagram. For sample preparations, all samples were cleaned in an ultrasonic bath with acetone, methanol, and deionized water, and dried with nitrogen before the experiments and before ablation. Diamond samples were also cleaned after ablation for 30 minutes in acetone, followed by 30 minutes in methanol in an ultrasonic cleaner in order to remove any debris from the ablation process. After the ablation, the samples were then spatter coated with a thin layer of gold to ensure good conductivity when viewing the samples by scanning electron microscope. بعرف شهر بتصلح ولا وايرلس ها خلاص هو مش مشكلة. No, I think it doesn't work. Thank you. ألف شكر لك. To estimate the structure depth, we used cellulose acetate films from electron microscope sciences for sample replication. This cellulose acetate material is 35 micrometer thick and soluble in acetone. For sample replication preparation, we cut out a piece of the replica material of a size suitable to cover the area to be replicated. Then a few drops of acetone are placed on the specimen surface and the replica film was applied immediately. Surface tension forces pull the film down against the specimen. No pressure is usually required. The film is left to dry for 30 minutes and gently lifted with tweezers. Once it has hardened, it then mounted on an SEM sample holder using carbon tape and then sputter coated with thin layer of gold for examination in the SEM. I'd like to show you some of the ablation results on diamond, this single crystal diamond. Ablation of the first figure we show is a sawtooth structure on synthetic crystal diamond surface created from a design containing multiple triangles, each measuring here 40 micrometers in height and 20 micrometers at the base. The structure shown here contains the 3 triangular wedges that taper down to a blunt tip within a few micrometers of the opposite surface. So this is the machined structure. We have the 3, 1, 2, 3 triangular shapes, and this is the replica we made to estimate the thickness of such structure. It is shown with a 45-degree tilt. The diamond sample which we have shown was irradiated 3 times at the initial working distance of the microscope objective with a pulse strain of 200 femtosecond laser pulses at the rate of 250 kilohertz with a pulse energy of 420 nanojoule. We used 250 kilohertz repetition rate using a shutter ablation time of 3 milliseconds, corresponds to 750 overlapping pulses, and the estimated height of the replica in the previous figure was 5.6 micrometers. So this gives the actual depth after the ablation with 750 overlapping pulses at a repetition rate of 250 kilohertz. The jagged boundary lines shown here are due to the resolution used in the machining process. The original programming resolution correlating to these shapes was set to 1 increment in test space equal to 1 micron in the actual space. Much smoother boundary lines can be created using smaller increments. The shape in figure 2 was analyzed for feature variation with a change in laser pulse energies as shown in this figure. We compare here 4 figures for the same shape ablated ablated in 4 different experiments. The first one used 0.4 microjoule, the second one 0.84 microjoule, the part C is 1.68 microjoule, and finally D uses 2.52 microjoule. If you look at the various shape, we notice that the tip of this region here becomes more round as we increase the pulse energy. Plus, the other thing we can notice is the area between the edge of these triangles up to here becomes bigger as we increase the pulse energy of the machining. Here is a magnified view, and we have labeled 2 distances, EE and SS, EE from edge to edge, and SS from surface to surface distance, and we show the results as a function of different pulse energies. So we see that the gap distance is we see that the slope of the patterns do not change with energy. What changes really is what matters is 2 things, as we saw. The distance, this distance increases with the pulse energy, and also the roundness of the triangle increases with increasing energy. Here, figure 7 shows the dependence of feature depth on laser pulse energy. Of course, this has been plotted from the replication data, from the replicas, from which we can estimate the depth. And we see here there is almost a linear relationship between the depth and the pulse energy. So this shows the dependence of feature depth on pulse energy for the shapes in the figure in the previous figures. We also formed periodic linear groves in synthetic single crystal diamond with femtosecond pulses at 800 nanometer as shown in A here. So A shows the same image of the groves obtained after radiating the synthetic single crystal diamond surface with a pulse train of 200 femtosecond laser pulses at a rate of 250 kilohertz using a pulse energy here of 1.2 microjoule. In this figure, the laser polarization is oriented horizontally perpendicular to the translation direction. So if the translation is in the Y direction, the polarization is in the X direction. In figure B is the replica of this figure from which we can estimate the depth. So this is the gold-coated extraction replica of the groves patterns from A is shown with 45-degree tilt. So to summarize this figure, we obtained it using a pulse train of 200 femtosecond laser pulses at a rate of 250 kilohertz using a pulse energy of 1.2 microjoule with a shutter open time of 3 milliseconds at each point. So there is an electromechanical shutter just before the objective, and we open the shutter for 3 milliseconds at each point of ablation. The step size is also important. The step size in machining of the groves was 0.25 micrometer, and the horizontal line spacing in the original programming of this shape was 4 micrometers. So the step size is only a quarter of a micron, and the distances between the groves were 4 micrometers. The resulting width, if we look here at the width of the patterns here, we notice that the distance between a grove to a grove is about 0.7 micrometer, which is lower than the diffraction limit of a spot. The diffraction limit can be estimated as 1.22 multiplied by the wavelength and divided by the numerical aperture. And if we calculate that at 800 nanometers, that would give us approximately 1 micrometer. So the width of the grove is less than the theoretical diffraction spot size. So the mean value of the groves were 0.7 micrometers with a standard deviation of 0.1 micrometer, and the minimum distance between the groves were 0.5 micrometer with a median of 0.7 and maximum of 0.8 micrometers. We also machined a star shape shown here. So this figure is a sim image of a star shape obtained after irradiating the single crystal diamond surface with a pulse train of 200 femtosecond laser pulses at a rate of 250 kilohertz using a pulse energy of 1.2 microjoule. So what we notice here is in this regime, the results show neither expelled liquid material at the edges of the structure, nor significant formation of debris on the target surface. So it appears to be, there is also no evident cracks in the surrounding material, which indicates the absence of high ablation pressure. So we obtained a fairly clean machining. It is also interesting to show that during the ablation process, we found induced nanoscale surface morphologies in the irradiated areas of synthetic single crystal diamond, as shown in these two figures. The first figure here shows the same image of periodic structures formed after laser irradiation with single pulses irradiated at each spot. The difference between the two, they appear to be similar, but in this we have 750 pulses, right, which corresponds to machining at a rate of 250 kilohertz with an opening, shutter opening at of 3 milliseconds. That corresponds to 750 pulses. So these nanoscales, in machining these nanoscales, the step size was 0.25 micrometer using an objective, 100x focusing objective with a numerical aperture of 0.9 was used to focus the 250 second pulses centered around 800 with an energy of 840 nanojoule per pulse. Also, the laser polarization was oriented horizontally perpendicular to the translation direction. Before I finish and draw the conclusion, I would like just to present here a Raman spectrum for the nano diamond. For an unirradiated nano diamond, there is a peak which centered around 1332 per centimeter, and we obtained this peak, this Raman peak, in an area where we didn't use femtosecond pulses. The first graph has the same location of the peak, but the intensity is 0.4, 40% relative to this one, approximately 40% relative to this one. So this means that after using the femtosecond pulses and cleaning the sample, what we obtain is a diamond also, not graphite or carbon. This is provided that we clean the samples. So in conclusion, we can say the most accurate and precise emulsion of design is obtained when ablating with relatively low energy. Also, we have used Raman spectroscopy to show that under respective laser parameters and post-ablation cleaning strategy, the graphite peaks are absent and the diamond structures retain the original diamond composition. Using pulse energies that are significantly above the threshold for permanent change, it is shown from this work that femtosecond laser micromachining provided negligible additional heating and shock wave damage. The upper limits on laser pulse energy, number of pulses and number of passes used in this study were 2.52 microjoule, 750 pulses and 3 passes respectively. And finally, I would like to thank you for giving me the opportunity to give this talk. Thank you.
We all thank Dr. Uthman for this nice information about the cutting of the diamond. Thank you very much. Any questions, please? Yes, Dr. Zakib.
Do you have the technology to do undercuts in order to make suspended structures in on the crystals?
We did not do it.
But
No.
Okay.
You mean
Yes.
internal to the material? Yeah, we never did it.
Here you are, please.
So far.
I was wondering in the diamond shape that you micro machined in the single crystal diamond, the object of the star. I couldn't quite see.
Scale was 40.
40 microns. Yeah. Okay, so roughly 40 microns. So overall, how long does it take to machine an object like that, a 40 micron star like that?
It takes approximately 20 minutes.
20 minutes.
Yeah.
Okay. Do you have any plans, or do you see any strategies for increasing the throughput for these things? Because that's, I mean, to make an object, 20 minutes an object with expensive lasers is a very, the throughput is very, very slow. So for actual production work, there has to be something, there has to be a solution to this problem.
Yeah, thank you.
The laser itself is slow in this process, you know. Lasers are not well performing in this technology, but still novel technology. Thank you very much. Any other questions, please?
I think, can I answer him? I think the main objective of this work is to study the characteristics of diamond rather than to make commercial production. So these samples were taken from a company that makes a single crystal diamond, and we have to do certain tests to improve or to give them feedback about their processes.
The results that you got were very impressive, but I was just wondering what the future would hold, and if this was going to be a kind of process which would, while being very impressive, would be essentially one-off structures that are always going to be somewhat expensive. That's all.
Sure, yeah. Thank you.
Thank you very much. We would like to thank Dr. Othman again. Thank you very much. Okay, we are now inviting Dr. Hussein Samara. Please here. محطوط هون ولا Okay, it's your turn. Thank you.
I would like to talk about on the use of sunshine-based models to estimate global solar radiation in Hebron City, Palestine. Let me introduce the subject. Understanding solar radiation data is essential for modeling solar energy systems because it is a non-polluting and non-depletable, and also it's reliable. Solar energy is not being used as a primary source of fuel energy until now. A largest research and development effort is underway to develop economical systems to harness solar energy and make it a major source of fuel energy. For many developing countries, solar radiation measurements are not easily available due to incapability to afford the measuring equipments and techniques involved. It is therefore important to consider methods for estimating the solar radiation based on the readily available meteorological parameters. So our target is to validate several expression models for a prediction of a monthly average global solar radiation horizontal surfaces from sunshine duration in Hebron City and select the most adequate model. Several equations were employed to estimate global solar radiation from sunshine hours. These equations included the original Angstrom-Prescott linear regression and the modified versions like quadratic, logarithmic, and exponential functions. Here we have the original linear model, which proposed by Angstrom and Prescott. H over H0 equal to A plus B S over S0, where H is the estimated global solar radiation, H0 is the extraterrestrial global solar radiation under clear skies, A and B as the regression parameters, where S is the measured sunshine duration, and S0 is the maximum possible sunshine hours. The other exponential model, also the same parameters are used in the four models. The regression parameters A and B are proposed by Tiwari et al. A equal to parameter, and depending on the latitude angle and the clearness index, S over S0, and also B depending on the same parameters, the latitude angle and S over S0. The extraterrestrial solar radiation, H0 equal to, depending on the solar constant, plus the number in the day, Dn, starting from 1 January to 31 December. Also depending on the declination angle, obtaining the extraterrestrial value by substituting the parameters, the declination angle and the day in the year. S0 is the maximum possible sunshine duration, that depending on the also the declination angle. Okay, after obtaining the values of the sunshine, the extraterrestrial solar radiation values, the data of the measured sunshine hours and the measured values of global solar radiation are provided by the Palestinian Meteorological Station Network Office for 48 months. Then, to compare the estimated values with the measured data, I have used the coefficient of determination and the root mean square error, and also the mean absolute percentage error. By obtaining the parameters by Riwari et al., the two equations of Riwari et al., and obtaining the extraterrestrial solar radiation, we have also the maximum, obtaining the maximum possible sunshine hour, S0, and we have S, the measured value of the sunshine duration. This is the normal distribution of the measured values. It seems that the maximum value at the end of June. And here we have, this is the average values of the 4 months in the year, for 4 years. And the same thing, the maximum, it seems that to be at the end of June. This is the measured values. And then by comparing the estimated values with the measured values, it seems that the linear model, as we see here, better estimates the global solar radiation in winter months, while the quadratic one better estimates that the maximum values in summer months. And as we see here, the exponential and the logarithmic model, as comparing all the results, we have here the results of the 4 models compared with the measured data. Also, as I said before, the linear model, the red dot, it seems that in winter months gives better estimates than the other models, while the quadratic one gives better estimates in higher values. Using the coefficient of determination, also the linear model gives the better estimates with 0.9 around 89 point something %, while the quadratic one also 98.7%, while the exponential model and the quadratic model gives, the exponential model gives a middle value, while the logarithmic one gives the lower coefficient of determination. By comparing also the Riemann square error and the mean absolute error, as I said before, it seems that the linear one have a higher values, Riemann square error values in summer months, while winter months have lower values, and also for the same thing for the mean absolute percentage error. To conclude, the results of this work clearly indicate that the main significance of developing empirical models for estimating global solar radiation on horizontal surface reaching the Earth for a particular geographical location. The differences between the results of different are quite negligible. The linear equation is best overall according to R square and root mean square error and mean absolute percentage error, and has a best performance based on the measured data at one station or location in Hebron. It can be recommended to use the linear one for simplicity.
Thank you very much, Dr. Dr. Hussein Samara. All we thank to Dr. Hussein Samara. Thank you. Any questions, please? Okay, thank you very much for your enjoyable solar energy scheme in Palestine. Thank you very much.
Okay.
Now we are inviting Dr. Zaid Kamhi.
Good afternoon, everybody. This work has been carried out by me in collaboration with Professor Klaus Wendt and Dr. Sven Richter from Johannes Gutenberg University at Mainz. In this talk, I'm going to talk a little bit about the topic, an introduction, then the development of the RELIS, resonance ionization laser ion source, and the LIST laser ion source trap towards higher selectivity. Then the principle of operation of the LIST and the construction of a LIST with the ion guide instead of a trap, then the simulations and the results and conclusions. Online facilities such as Trellis, Lisol, Igisol, Isolde, and others all seek high purity radioactive ion beams for studying exotic nuclides. Already more than 6,000 nuclei have believed to be exist, and scientists are still looking for more. The traditional way to study such exotic nuclides is the mass separator, but it has a major drawback, which is isobaric contamination. As a solution of this, we have to look for efficient and selective ionization, followed by mass separation, which is the origin of RELIS, resonance ionization laser ion source. But there are some surface ionized ions which cannot be deleted except by using another technique, which is the LIST, the trap. The surface ion source is an unselective ionization. It ionizes all metals in the hot cavity. When entering to mass separator, isobars go at the same location. They are not resolved. So we have unselective surface ionization in hot cavity, and isobaric contamination still influence the study of exotic isotope nuclides. As a solution, the resonance ionization laser ion source with selective ionization can be used in combination with the mass separator. So the laser is shot and it ionizes the element of interest selectively. So we have high efficiency of the element of ionization of the element of interest, but still no suppression of the isobaric contaminations. This can be deleted again by using another trick, which is applying the trap with a repeller. The repeller reflects all ions created after the hot cavity, so only neutrals enter into the ion guide. When the laser hits those neutrals, it ionizes only the element of interest. So we are suppressing the we are suppressing the contaminants by the repeller, and we selectively ionize the element of interest, but we have to sacrifice some ionization efficiency. In an offline experiment done in mines, this was tested, and it's clear in the red signal that the natrium, sodium, and aluminum nuclides are deleted, which means that the list has successfully suppressed the contaminations when we are studying magnesium. The principle of operation of the list is very simple. So we have the repeller, the red colored plates. It repels all ions created after the atomizer. Only neutrons enter into the trap, which is segments, metallic segments, with a potential drop that leads the ion to cool down until it is collected in the trap. And the potential barrier is put there so that they are trapped in that point. Once we need them, we remove that potential barrier and we extract them into use. The major advantage of this trap is having a low emittance radioactive ion beams. But because of using the high pressure of about 200 millibars, which is not favorable for the people working with online facilities, the travel time is going to be long. So we cannot, by the trap, detect or study the nuclides less than 100 milliseconds. So to solve this problem, ion guide instead of the trap with the ion guide is suggested. In iSolde, the construction is composed of several parts: the laser, the magnetic separator, data acquisition system, and the ion guide, in addition to the energetic ion beam and the nuclear interaction with the hot cavity. So this ion guide has this layout. It's composed of radio frequency rods, 4 rods, and the exit hole, the entrance hole, which is the repeller also, and the extractor at the end. So for making simulation, we have to use a software package, and we used Semion version 8.1, which studies the motion of charged ions in electric and magnetic fields, and it determines the electric fields and the ion trajectories by solving Laplace's equation. But before making simulation, we have to make a geometry file by Semion, which reflects the composition of the electrodes. Then we have to assign the potentials to every electrode. In addition, the initial conditions have to be given, which is the kinetic energy of the ions, the radio frequency used, and the magnetic field if present, and the collisional effects if the pressure is high. The first thing we have done is the structure of the list. In nature, the list looks like this, while in Semion, it's done like that. And to see if the components are really in, we have to take a cross-section. So a ZY cross-section is shown here, and the rods, 4 rods are these. The repeller is here, and the entrance hole, and the exit hole, and the extractor. And we always use the extractor with minus 12,000 voltage. In addition, we have assigned this plate, the end electrode here, just to count the ions which can reach this point. In reality, it doesn't exist in online experiment, just for simulations. The first thing we have done, just to add a potential to the repeller. without any radio frequency. So at the beginning, we have assigned minus 50 volts, and we see that the ions can pass through. With minus 20, also they can pass through. With minus 10, they can pass through. When we reach plus 4 volts, the ions are completely reflected. So it works very well with voltages above 4, such as 10 volts, for suppression of isotope contamination. Using the radio frequency of 1.2 megahertz, the radio frequency is applied to the rods. In addition to a DC voltage. So we play around with the potentials given to the repeller and the case and the exit hole. If all are at 0, we see the triangle of stability is like this. It's DC voltage versus radio frequency amplitude voltage, and the color is the percentage of the ions which can pass to the extractor. So the red color is high percentage, which can reach to 100, and the dark colors are reaching to 0, the black colors. In addition to this, which is the stability triangle, this picture shows us where the ions are lost or where they splat. So we see some reach the extractor, and the ones which are lost, they are splat at the rods or reflected to the entrance hole. With the second situation, minus 50 volts applied to the repeller, with the others 0, we see very low stability.
لسه انا بحب استخدم اللابتوب بسوي ولا ليش ما بستخدم
So with the potential minus 50 is applied to the repeller, we saw very low efficiency everywhere. With the case minus 50 in addition to the repeller, we saw enhancement of stability, but still the ions are lost on the same position, the surfaces of the rods. And the fourth, we have higher stability with all set to minus 50 volts. So to compare them all together, so we see that the worst case with the repeller at minus 50 and the highest at minus 50 for all electrodes. We checked the effect of the kinetic energy of the ions at the beginning, at the entrance of the ion guide. So increasing from 2 electron volt, 3 electron volt, and 4 electron volt. And we noticed that ions with higher initial kinetic energy are more stable through the list, which is very logical. If we change the angle at which the ions are incident, we have done that by applying a cone angle, and the ions are randomly changed within this cone. If the angle is 0, so they are axial, they move with very stable condition. If the angle is 10, it's very stable. 20 degrees, it's gone. 20 degrees, it's less stable, and 30 degrees, it's the worst.
وين الشق هذا؟ شو اللي وراه؟ مش موجود؟ أي موجود. طلع من السيستم. السيستم وين؟
So the ions with higher initial kinetic energy are more stable through the list. If we change the initial cone angle, we see that as the initial incident angle of ions increases above 10 degrees, the stability decreases dramatically. So we just play around and put 10 plus 10 volts at the repeller, 0 at the case, and 0 at the exit hole. And we see how the potential inside the system is. Equipotential lines are shown, and we see how the potential drops from the entrance, drops slowly inside, and when reaching the exit hole, it drops very fast until it is minus 12,000. This can be shown in this curve. So it is almost stable, it's decreasing slowly inside the rods, when outside it is dropping very fast. In semi-ion, we see how the potential drops also, the same thing, but if we zoom in, we see during the first 4 millimeters that there is a potential barrier. That's why the ions with low energy at the beginning cannot pass through this potential barrier. If we calculate the ion speed by semi-ion, we see that the ion at the extractor has the speed of about 37 millimeter per microsecond, which is 237,000 meters per second. If we just estimate that time for that, it is a few tens of microseconds, which makes the list suitable for short-living isotope studies. If we study the effect of the position of ionization, so if we take 4 millimeters from the exit, the entrance, 20, 30, 50 millimeters as examples, and we see how the stability is. And we noticed that at Z 4 millimeters, ions pass. Below this, ions cannot pass. They are reflected as we saw at the beginning. So ions created at Z greater than 4 millimeters from the entrance can most probably survive. If we change the mass, 41 atomic mass unit, 50 atomic mass unit, 67, we notice that we go to higher stability with higher masses. And if we notice that for the mass 41, we have radio frequency about 300 and DC 45 volts. For higher masses, these potentials are increased. For 67, for example, it is 500 radio frequency volt and 75 DC volts. So as mass increases, the DC maximum and RF maximum voltages also increases. Since the ions splat at the surfaces, we thought of having very thin rods instead. So we have done this simulation. We have 1 millimeter rods, 12.5 millimeters from the center, with the same voltage settings, 10 volts at the repellor and 0 elsewhere. And we see very similar potential drop as seen before, and similar travel time also, which makes this suitable also for short-living isotopes. In addition, with the same thin rods, we studied the creation of ions or the travel of ions and stability at different positions. Z 4 millimeters, 10 millimeters, and 30 millimeters. And we noticed that the first thing, that the radio frequency increases up to 1400 volts instead of 500 or 300. So we have higher stability. We have higher DC voltage and RF voltage as well. In summary, LIST with ion guide can be a fantastic tool for studying short-living exotic nuclei. Suppression of unwanted surface ions can be achieved by applying a positive potential above 4 volts. Large masses are more stable than small ones, and large masses can be studied by higher DC and RF voltages. Ions created within 4 millimeters are repelled, while created elsewhere can pass through the system. As the initial incident angle increases above 10, the stability decreases dramatically. Using thin rods can be used successfully for studying short-living exotic isotopes with higher DC voltage and RF voltage. Thank you.
Thank you very much, Dr. Ziad Kamheen. Any questions, please? Yes. Here you are.
Well, I'd like to say that this was certainly a very interesting talk, and I'm very pleased that you could reach the end of it before the wireless disconnected again. I was wondering if in your studies you had considered the effect of space charge on these ions, because very often space charge can modify the potential lines or the equipotentials that you think you have, and also the stability of your trajectories that you think that you should have. So the question is, space is when you have
space
a
charge,
dense number,
for space charge, if you have
ions.
very large numbers of charges, then you have to consider it. If you are talking about low production nuclear reaction, then you don't consider such thing. Well, our studies is mainly directed towards nuclear exotic nuclei, which are produced very low percentage.
Yeah. Well,
We didn't consider that actually.
When you make your initial ionization pulse, you get a cloud of ions, very localized, spatially localized cloud of ions.
Yes.
And this actually produces a potential, okay, a voltage.
Yeah.
And this can modify the lines of force that you calculate in order to get the performance of your
Yeah, it will
system.
mainly.
So that this is
yeah.
my only question. Sometimes this is important, and sometimes it's not important. It's
In this study, we assumed 2 electron volt from the hot cavity.
Yeah.
In addition, I made if the energy is increased, it's going to be better even.
Yeah. Yeah, there's something called the Child-Langmuir law that you can use to estimate these things. Okay, thank you very much.
Thank you. You're welcome.
Thank you very much. Thank you. Any other questions? Okay. Thank you very much, Dr. Ziad. You are welcome at our university. Now, in the last session, few minutes, we will be enjoyed to listen to Dr. Ahmad Helmishtad. Please.
شكله بتعمل وايد سكرين بس خليها كملي خليها كملي. السلام عليكم بسم الله الرحمن الرحيم.
Bismillah. What we're trying to present today is this little research that I did toward my master degree in Al-Quds University. My supervisor was Dr. Uthman Zalloum, all thanks to him. Also to Dr. Muhammad Abu Samrah and Dr. Khalil Dabaini for their research that I get benefit out. This topic, in this topic we're talking about the gamma ray measurements of soil samples from southern parts of the west of Beit Lahem up to southern parts of Hebron in Palestine. We tried to get the concentration activities for terrestrial radionuclides, also to contamination radionuclides that due to nuclear activities and industries. We talked in chapter 1 of that thesis about the gamma ray. We talked first about gamma ray as a physical phenomena. The physical theory behind it, starting by the classical point of view, ending up to quantum theory and the quantization of gamma rays, or looking at it as as physical quantas. Then we talked about gamma radiation interaction with matter that relates to the detection system that we used, which is the sodium iodide doped with thallium detectors. Also, it concerns the shielding materials that could be used to protect mankind from gamma radiation. On the other hand, discussing this interaction, these are the main reactions that gamma rays made with any material, starting by solid materials, ending up with living materials. The photoelectric effect compensating per production fluorescent X-rays. Then we talked about the biological effects of radiation. We all know about that, and how does gamma ray affect living things. On the other hand, how it could be used to cure certain diseases like cancer. And we found that, or we said that it is not preferable in curation of cancer. We collected our samples through these situations, as we mentioned before. This is the maps, and these are the addresses of the locations we took our samples from. We used this setup, which constitutes of the sodium iodide detector that we talked about. We have a multi-channel analyzer and connected with a computer system that will hand us a spectrum of those gamma rays that fall on the detector, which could be seen here in more obvious form. This is where the gamma rays falls on and react with the sodium iodide detector or material. Then it will cascade into certain levels of signals, will be captured by this dinode, multi-dinode series. The signals amplified, handed to the multi-channel analyzer, and will be arranged all over the range of gamma rays, which starts by 100 kilo electron volts to about 3 mega electron volts. Now we talk about calibration of our system. We calibrated our system using a source or a reference source that contains these nuclides with these activities. It's known by the source. Depending on that, I have to calibrate my system to be able to get right spectrums for my samples. This is how the spectrum was measured. These peaks were used to calibrate our system for taking our measurements. We have also to build up the efficiency of the device, of our device, relative to the reference we used above. This efficiency will help us calculate the activities depending on this curve or behavior. We can see here the background measurement. Background measurement is just how you can get these, what the device can measure without any samples being doped in. Now, we start chapter 3 by calculations, and here we calculate several standard values. This is the activity. In general, we have to calculate for each peak that we can diagnose in our samples. These values are equivalent, which is how can you estimate the radiation or the concentration activity caused by radium due to the main terrestrial radionuclides series, which is U-238, thallium-232, and potassium. These values were measured and calculated in our samples. The absorbed dose rate in air was just an estimation that is caused by these radionuclides that exist in the soil and in the building materials or around us. This is the same equation of the absorbed dose rate, but including the cosmogenic radionuclides and gamma rays causing the atmospheres to get radiated, plus the contamination element cesium-137. These are just indices, which are rational numbers relative to worldwide standards of safety for radiation or radionuclides. Now, the main three chain series is like uranium 238, thorium 232. شيء These are the three main chain series. These are the daughter nuclides of each of the main or of the parent nuclides, which are thallium, uranium, and uranium-235. In measuring radioactivity, sometimes, and especially in these series, you couldn't measure